Waiting for Twitch to catch up as usual. Any second now. There we go. Okay. Welcome back, everyone. For the third stream this week, it's been a busy week. So, last we left off yesterday, because I did an additional stream yesterday that wasn't planned. That was supposed to be a short stream to just finish up something I had started on Tuesday. I ended up streaming for 6 hours, something absurd. But we made a lot of progress on the IR lowering yesterday. And as a result, this evening will be about continuing and trying to make as much progress as possible on the IR lowering. We arrived at the point yesterday that this kind of silly example code was properly translated into something that looks like this, with like labels for go-tos and everything. So this evening we're gonna continue doing more of that, start doing register lookups and so on. And I also want to start, I think, by something that's not the most urgent, but which is going to be fun to do, which is going to be to do block merging and block pruning to reduce the number of labels that we output in the final code. So yeah, let's get started. So the thing I've been wanting to do that I'm going to start with, which is not the most urgent and not the most important, but I think will be fun to do, is going to be, again, I want to do block pruning. At the moment, when we try to process a block, to detect whether the block in which we are is reachable or not. Actually, come to think of it, I think there's a bug I'm seeing right now, which is not the thing I was planning to do, but I saw it immediately. Let's start with that. There is a bug here, which is that I do not check that the block is reachable before processing the first statement, which means I could start a block I could process a statement in the block that's actually unreachable. So I should start with this. Am I in a block that's reachable? If not, then what do? We end the current block. And when we have some diagnostic reporting capability, we'll emit a warning like, hey, this code is unreachable. But for now, that's unimplemented. Okay. Otherwise, we are reachable, therefore we can process the next statement. And after that, we can check, are we in a block still? Meaning we are still processing statements. Perfect. We can go recursively process the next statements. Otherwise, we are not in a block, which is fine. It means we have finished processing the block, we're done. But if we are in a situation where there are still some statements to process, then we should emit a warning there again. Okay. So here is the thing. We are identifying that a block is not reachable. That means it has no parents. And we immediately end it, and that block will never be processed again. So one thing I would like to do is to not include it in the result of the lowering thing for a function, so that the function at the end does not contain that block. The other thing I'd like to do is see if there are ways to do block merging. When I have a block that has only one parent and its parent only contains a direct jump to it, then the two blocks can be merged as one and grouped together, which reduces the amount of code to generate. So I think what I'm going to do is do both. At the top here, lower function, at the moment, I create a function by just getting a hash map of the blocks. What I'm going to do instead is to create an ordered list of the blocks in which the first element is the starting block, with the blocks ordered as much as possible in an order that makes sense. And this process of doing basically a topological sort of the blocks will allow me to do both the pruning and the merging at the same time. So we are going to do that. But to do that, there's a few changes in representation that we're going to need. So let's go to the AR. First, I think it will be good to know, even though that's not technically something that's required for the code generation phase, I think it would be useful to know the parents of a given block, which will be a list of label. And I think, even though there's going to be duplicated information, I think it will be useful. Do I do that? I was going to say, I think I want the blocks to have their name, their own label in it. Like a block should know its own label because that's a property of the block. The downside of doing this is, since I'm going to be doing hash maps of a label to block, that information will be duplicated, and as a result, if there's a bug in my code, there's always a risk of that information being incorrect, which would be annoying. But I think it's still useful overall to have the name of the label. Unless I don't do that, and instead, yeah, I think I'm not going to risk it. I'm not going to do that. And instead, a function will have whatever is the name of the first label, but the blocks will not be that. It will be a non-empty list of tuple label block. There we go. I think that's better. So by definition, something that is ordered. Okay, so now that the parents are also stored, and I'm going to make it, I think, the first argument, the first field of thing. Which blocks are we coming from? What are the arguments being given? What are the instructions? And how is the block closed? That's basically the order in which that information will appear. Except this will not be displayed in the LLVMIR, but you know. This means I can make a few changes to the lowering monad. First, I do not need to keep the parents there because the blocks here will contain their own parents. But that is fine because since I have isolated all of those implementation details behind some functions, I just have to modify the functions and everything else should work just fine. So parents for a given label will be, let's look at the blocks. Actually, I might. No, it's fine. Okay. I will probably want to just use the same thing I've done for other block properties. Like block info here. Yeah, I don't have a lot that takes information from the block at the moment. But maybe that means I need to resurrect those functions. Okay, so the parents will be, for a given block, it will be get block info of the given label, and then we fmap block parents, I suppose. current parents will be, yeah, current block parents. That hasn't changed. This one I still don't need. And register parent will still be something like this. This will be closer to one of those. The block info for that label will be modified so that block parents is modified to include that one parent as well. Parents are not ordered, so I might actually do this to insert it at the beginning of the list. Okay. So that then everything else should work just the same. Let's check that I have here something that looks at the parents of a given. So this is going to be yeah, this is just doing that operation on the result of parents of the label. So we get the parents of the label, which is always going to be, it's always going to be a list. Here I need to make sure that the default block does contain block parents as an empty list. Okay. So parents label will give me the parent information of that particular block, which is a list, and I am only interested in not null. And I can probably write it like this to simplify a few things. Okay. That's fine. Let's just actually check that this compiles before I move on to the rest of the stuff I want to do with this. And I think that's the only issue. Yeah, perfect. So here at the end, I've said that now a function is a non-empty list of blocks. This is still a hash map. This doesn't work. Okay. So let's go back here and let's do the block export function then. And this function will be what we call here, and will create the list from all the blocks. And we start at the start block, which is always going to be the first one. Okay. Now, the thing is, here I'm giving it as an argument. I will probably want to make that monadic in some way, because I'm also going to need some set, because there might be loops in the graph. Actually, how do I implement the topological sort? Is that just a depth first search? I don't remember what algorithms exist. Okay. So for all elements in the set, add that an element to the list. Ah, I see. Set of all nodes with no incoming edge. I see. Okay. Okay, so that means at every step. Okay, I see how to do that. That's not too complicated. Oh, but that is only for graphs that do not have cycles. Okay, depth first search. Actually, do I really care about it being a proper topological sort? Is that really... I don't actually care. Hmm. Let me just think about this for a second, because a proper topological sort would be the most intuitive to look at, but I don't really need that to be the case, is the thing. Let's see. Yeah. Okay, so I'm just not gonna bother. I'm gonna do this the naive way, and that'll be fine. Which means I'll probably do that as a depth first, I suppose, then? No, a breadth first, I think, will be what will be the most satisfying to watch at the end. Okay, so that means I need to keep a list of the things to visit. List will be an absolutely horrible container for this. I will there again, want a better container at some point. Some kind of DQ would be better. Actually, might as well do it now. I think a sequence is what I want. So, okay. Let's write this. I'm gonna make it that in another module so I can just like write things in a slightly more clean fashion. This will be part of the lowering. This will be the collection part of the stuff. I'm gonna want data sequence. Qualified as S, I think. Maybe as L, because I will probably also want a hash set. Okay, so collect blocks will be the top level function, which will be the API, which takes a hash map from label to block and a starting block, which is the label that identifies it, and returns a non-empty. list of tuple label block. This will be running in a monad, which is gonna be local to this file and not exported out of it and implemented. There we go. Which I'm gonna call the collect m, which is gonna be a reader t of the hash map label block on top of the state t. And here's what we're gonna need to keep track of. Since this is gonna be a breadth first search, we're gonna want to keep track of where do we go next, basically, things we add to the list of things to process. And we're going to want to keep track of a set of the things we have already seen to deal with cycles. So do I want to make a dedicated struct for this? I think I do, just so for readability. The collect state, there we go. The collect state will be a queue, which is going to be what labels to have a look at, and which is going to be a sequence of label. And it's going to have seen or visited, which is going to be a hash set of label, the ones we have already seen. Okay, that should be everything we need to do this. So to collect a block, I'm going to introduce run collect, that given the hash map from label to block will, and actually this is a state, not a state t, and some action in the collect m monad will return that a value. And we do that by doing a, so that's blocks action, we run the action and we remove the reader, so flip run reader t of the blocks, and flip exec state t with the starting state, which is going to be a collect state, in which there is only one label to visit, the starting label, and we have seen none of the labels yet, so our visited set is empty. There we go. So collect blocks will be a run collect of, I suppose, just visit starting block. So I'll need here blocks and start, and this is going to be a run collect of visit. I have to underline visit start. Well, of step, I suppose. No. Okay. This is going to be a tiny bit more complicated. It's going to be a run collect of while m well, not exactly. What I'm gonna do is, I guess it is a while m. No, I think it's an unfold. Let's have a look at control monad loops as usual. Because I want to, as long as an action occurs, I want to do something and I want to collect the result. That's an unfold. Yeah, I guess I can just do an unfold of visit and visit will perform the check for me. Yeah, that should be fine. So that will be an empty from list, which will crash if the thing is empty. So I will probably actually want to two non-empty at the end. So it's going to be a two non-empty of run collect of while m. Sorry, no, unfold m. What's the prime version? Plus. Is that monad that is monoid as well? Yeah, okay. But here I don't want that. So unfold m of visit or step. Okay. And y is two non-empty. I guess here what I'm trying to encode is this function cannot exist if the hash map is empty, basically. This function will just have to panic. Do I want to make that as a nice, or do I like not even want to bother? I think I don't even... I should probably make it properly. I think it's fine to have partial functions every now and then that just don't... it's fine. For now, this is going to be a from list. Yeah. And this will crash if the list of blocks is empty. That's fine. Okay, so that's most things we need. So now let's define this step function that will give me, in this collect monad, one tuple, label, and block. Well, it's going to give me a maybe of one such thing. What do we do at every step? We look at we get the state, we get the queue from the state. So the collect state will be gathered from the current context. If there is at least one element in the queue, I never remember the syntax of sequence. Oh, there are patterns. Okay, perfect. So I can match on empty. If it is empty, then we return nothing. There is no longer any block to process. This is the end. If we get some label at the beginning of a list of other labels, this is where we do stuff. Because in this case, we have a thing to visit. But we need to check still, have we already visited it? So if label is a member of the visited set, then I guess I should always pop the label, because either we process it or we skip it. In either case, I will want the CSQ to be set to what's left, which is labels. So I've popped the first element. Is there actually a... That's fine. Now, if it's already a member of the visited list, there's nothing else to do, and I just call step recursively to try to then go to the next element that we have not visited yet. Otherwise, what do? we have a label. We have not visited it yet. So now we should get a block information by doing an asks of our reader. And what we're going to ask is lookup of that label on nothing report ice. Because that means that we have a label we decided to process that doesn't appear in our hash map here. So that information is inconsistent. Now, okay, we will want to do... Let's do things properly. To non-empty is gonna be a it's gonna be which one is it that gives me a proper maybe thing? Actually, I'm just gonna do it as a like this. If I get some normal list, then I can create a non-empty list that has this shape. If I get literally anything else, then I can do a report internal compiler error. Okay. And I'm going to do the same thing here. In a sense of like, oh, we're trying to get the information from the hash map about this block that we have to process. And found this is a bit verbose, but this beats having a bunch of like panics in the code. Something is wrong with that syntax. We will figure it out. The formatter is unhappy, which is a sign that something is wrong with the syntax somewhere. So here, block info not found. Block info would be all of this, and missing block will be the show of the label. Ah, no, it's not needed. Okay. So at this point, we are here and we have updated the state to we have removed the label we're currently processing from the queue. We have checked that it was not visited yet. We have and we have obtained the block information. I'm just going to rewrite a few things here, I think. Just because this is starting to be a bit verbose and I don't like it. I also don't want to like keep a copy of the state here because it's already outdated and there's always a risk of using something that's outdated, so I don't want to do that. So I'm going to introduce some helper functions to reduce the indentation and to make things a bit cleaner. So what we're going to do is instead use the to queue into a case if it's empty, pure nothing, and if it is label at the beginning of a list of a sequence of labels, then we do, what do? We set the state like so, and we go visit that label. I guess here would be a good option. It would be a good option to just like basically what I want to do is for visit to signal to me if anything was done, and otherwise a call step again, basically. How do I do that? How do I have visit signal that something has happened? Or do I do the check here at this level? Maybe I do the check at this level. Maybe that's the easier solution. So here I'll do an if m takes something then the else, and the if the test that we do is uses cs visited, which is the state that contains, which is a set of things we have already seen, and the function we apply on it is this label a member? If the answer is true, what do? We step recursively again. And if the answer is no, we visit the label. And visit is going to be this do block here. Where with all of the indentation reduced, there we go. Where the first thing we do, oops, is to modify the set of things we have visited to insert this label. Then we get the block and we report an error if we don't get that information. If we were not doing the merge, what we would do is basically at the end pure just of that label and block. But we might want to do more than that. But there's one more thing we need to do, even if we don't do the merge at all at the moment. We need to look at the block terminator to know, which means I don't think I need to do that. That's fine. I need to know where do we go from that block? Which block is the next block from this one? And that is going to be obtained. I need to do a list of the children as opposed to the parents, which is going to be a case of the block terminator of the given block. And that is going to be one of those. Either it's a jump or a branch or a return or a panic. In a case of a jump, do I want to handle each case separately so that I can deal with the jump case? Possibly, maybe not. For now, let's do it this way. So jump to a child the list of children is that child. That's an unconditional jump in a branch between child 1 and child 2. The list of children is child 1 and child 2. If it's a return, it doesn't matter what we have here. There is no block to jump to. If it is a panic, there is no block to jump to. So I have the children now. And I can modify the queue, which is CSQ. I modify it by doing, what is the sequence thing? Is it append? Oh, it is just a monoid and a semi-group, so I can do that, I suppose. So it's just appending at the end with sequence from list of the children. So, okay, we've visited this node. We've added this block. We've added its children to the back of the queue because we're doing a breadth first search of the blocks. And just that, this piece of code, if it works, of course, will perform, like, will already prune blocks that are unreachable, because we'll start with the start block and we will like traverse the tree basically and output them in an order that's like somewhat consistent with like somewhat logical. Oh, there's there's a thing I hadn't thought about. There's something I haven't thought about. Here I am assigning a label to everything in the my code generator assumes my code generator will assign addresses to things in a linear fashion. No, it's fine. It uses strings. So as long as, yeah, okay, it's fine. Ignore me. So I'm just going to do one thing on this. I'm going to do a find retrieve block function that, given a label, will perform an operation in this collection monad that gives me a block. And retrieve block is going to be this thing. So that all of this implementation detail of actually the thing might fail will be hidden in a dedicated function. If I do this, are you more happy? I don't have the blocks, nor do I have the label here. I have the label, and the blocks will be... So actually, let's go get the blocks, all of them. So that's just ask, and I do a lookup of the label in the blocks, and on nothing of that, I report an intercompiler error. There we go. So now this becomes retrieve block of the label. Now, okay, with that done, there is one more thing I'd like to do, which is, in some cases, it is possible to just merge blocks together. And that is when a block ends in an unconditional jump and the next block has only one parent. So they can just be merged together, basically. And I probably want to do that first. I think I need to do a separate function because I will need to do that recursively. So I have the label, I have the block, process label block. where process label block is this function here. And this is where I'm going to start by looking at, can I merge the thing? If yes, merge it and call process recursively, basically. So here, getting the children, that doesn't change. However, here's the one case I'm interested in. I will want, if there is only one child, I will want to look at its block and see if it has only one parent. So do I want to make that as part of this? Because what I'm doing is basically I'm doing another case of the jump, basically. Maybe I'll do that as a first. I'm going to do twice the same thing, but that's fine. So here, I start by the case of the Terminator, and oh, could I make that? Could I use? I can probably merge it. Let's not merge it for now. I want to do things one by one. So in the case where my block terminates with just an unconditional jump to another block, and retrieve block child label, and in the case where if the length of the block parent of the child's block is 1, which I guess I can test even just like if the block parents of the child is this one, basically, and nothing else, then I can merge the two blocks. Then the result of the entire function of processing that label and that block will be changed instead to processing that label and a new block, which will be the result of merging two blocks, which I'm going to write as a separate function, merge block child block. And otherwise, I probably want to move. Yeah, okay. I'm trying to see how to structure this in a way that's readable, basically. So I can already write the merge function, I suppose. Because the merge function will take block 1, block 2, and we'll return a new block. Okay, just gonna. Something is wrong with my indentation. The code isn't happy. Probably because I have something wrong somewhere. That's fine. Let me just do the usual and open the thing on top here. I want to look at what a block is. That's what it is. So basically, the result is going to be block 1. So we keep... let's do this explicitly. The resulting block that we are creating from scratch, its parent will be the block parents of block 1. because that's the one we arrive from. The block arguments will be the one from block 1, because that's where the starting point is. The block instructions will be the concatenation of both. So it's going to be the instructions of the first one, concatenated with the instructions of the second one. And the terminator, however, will be the one of the second block. And now we have merged the two blocks and we can proceed recursively. Now the question is, how do I avoid doing this case block terminator twice? How do I make this a bit more readable? And I think the solution will be oh, I see the syntax is also wrong here anyway. This will be, I guess I just do this test as part of this. Yeah, I'll do that. So here I'll do, in the case of an unconditional jump, this is where child label, I'm gonna do basically this. Look at the child block. If its parents is only this current label, then what I return is going to be a left of the child block. Otherwise, right of the child label. Oops. Okay. And in all three other cases, this is just pure of that. Nothing else needs to happen. And I can even go a bit further. And now, actually, I'm going to be explicit. It's better to be explicit. If I change my terminators, I don't want to make assumptions about the shape of this. I'm almost tempted to actually that and keep this case as the special one. There we go. So now, at the end, I get either left the block that I should merge with, or right the list of children. And that means here I can do a case of the children info of if I got this left child block, then I'm gonna do this process recursively with the label and the result of merging this block with the child block. And if I have a list of children, otherwise, then I do this thing. I add them to the queue of things to process, and I return the block that we want to keep. Okay, that should be everything. That should be everything, and that means now, with this, assuming that it works, which it doesn't yet, but you know, that means I can go back here, and this is gonna be not export, how do we call it? Collect blocks. Collect blocks, and it takes the hash map, all blocks, and the start blocks. There we go. Okay. So for now, this is what this file compiles to all of those blocks. Now we should hopefully remove block 1, which is unused, and therefore should not appear and should never be seen, so it should be pruned. And several blocks could be merged, like jump, target 4, there's a bunch. But this... no, there isn't actually anyone... Because this one branches, this one does a return, this one does a jump to 4, but 4 has more than one parent. This one branches, this one branches. There isn't a lot of there isn't a lot of direct jumps that can be merged, interestingly. But we can probably find an example afterwards. Okay, so first, let's make this compile. Okay, in collection, I don't need the AST. Nothing is happening on the AST. This is all IR. So I can remove the ambiguity. Empty. Or control lens. I'm not using lenses much in this thing. Just gonna hide empty. Actually, I forgot to use template Haskell here and make lenses on... Actually, yeah, I'm using the lenses absolutely everywhere, so I'm gonna need to do make lenses of collect state. And I should probably move all functions that use... This one actually doesn't use the lenses. I guess the only one that uses the lenses is this one. So I should move this function at the bottom of the file. That is one major downside of the template Haskell lenses generation. It makes the declaration order matter. Okay. And run collect now is no longer in scope, but run collect and run block and retrieve... No, yes, neither of those use lenses. I can just move them before that. Unfold M is from import control monad loops. And step, okay, that's annoying. That is very annoying to the point. No, I'm still having lenses for this, for the state is still so useful. I'm just gonna do this thing. I'm just gonna sort those functions. What bothers me is I really like to have a top-down thing where the first function in the file is the API and then everything else is the implementation details. But the lenses here kind of force me to do this the other way around, where this depends on step, which depends on the lenses. So step needs to be defined first, so it ends up being the other way around compared to the rest of my files. That is a tiny bit annoying. And I can put those in between here, I suppose. And remove all of the empty space that's not required. There we go. Empty do block. Interesting. Oh yeah, because they left this. It's no longer required. I guess instead of doing the left-right thing, I could instead introduce a finalize function that, given a label a block and a list of children does update the queue with the children and returns pure just label and block. Can I omit the just here? I think I can, because I can probably... Because that's part of the process thing, which is here, and I can just indeed just... There we go. And so in the case of a branch, I can finalize with the label and the block. Actually, if I make visit its own function, separate from step, then I don't have... Okay, let's clean that even further. Up. I'm gonna make step a dedicated function. You're gonna go here. And I'm gonna have visit be a function as well. That given some label does the thing. And that way I always have the label in scope, which makes a lot of things easier. Like, I don't have to give the label to process, for instance. So process doesn't take the label. Finalize doesn't take the label. Okay. And in the case of jump, I look at the child block. If it is an only child, then here I process with merge, not merging, merge of the two blocks. And otherwise, I finalize the block with the one child label. I'm just gonna say child just for brevity here. Sorry, let me see if this is important. It is not. Okay, and now I can remove this. And I have this visit function be a tiny bit more organized. Now, what are you unhappy about? Let's see next. Parse error. Yes, there's two else's here. The last statement of the do must be a... Oh yeah, of course, here I don't get the children info, I just do the case. And that's about it. Block arguments, there is a typo. Collect blocks is from collection. Collect state is right there. Because I put a comma here, which is the wrong syntax. Oh, and Q is... that's not gonna work. I don't think sequence is an applicative. I don't think I can do... Ah, maybe it is. It is. So I can do a pure start there. Okay. Expected, a function that given some... because it is an exact state, not an exact state t. And it's an eval state, not exact state. I always get them confused. Okay. And here, there's 3 arguments to branch because branch also takes the register, which I ignore. I don't care about it. This is not the point. A typo somewhere. There we go. And is that everything? Almost. Visit calls process of the block. I probably have a process that calls, no, it does call merge block here, okay. I wonder if I actually don't need to do the just as part of this as well, and I could just do it here. Yeah, I can just do the just here. Which means I can make visit just return the tuple, and I can remove just from here, which means this becomes process of retrieve block. Okay. What is wrong then? Process is applied to too few arguments. Oh, this takes label, which is not correct. And this might, as a result, influence the type of this. It might be the reason why everything is wrong. And there we go. And I suppose there's something here that doesn't return something in a monad. Yes, here this pure is incorrect. Because if, yeah, all of those, both of those are in the monad. There we go. Now, yes, of course. Those are not labeled, they are targets, so I need to extract the label from the target. That is what I'm interested in. I do not care about the arguments. Which means here that remains the same. I'm just going to remove all of this empty white space in favor of something like this. And likewise here, this is going to be the target label from the child rather than just the whole target. Actually, I could use a view pattern here. Because I only care about the label. So I can apply that on the argument, and I can do the same thing here. And here. Which means I can simplify this to being that. There we go. Okay. So run collect is missing something. Because run collect takes the hash map, the label, and the action. So it takes blocks and start that we're missing. And now I have redundant imports, which I love to see. That means I'm down to warnings that should be this binding shadows an existing binding from lenses again, hiding children. Okay. And now start block is applied to too few arguments. It is start label, not start block. And now this should compile. Oh, almost. Oh, of course, yes. This is no longer correct in my debugging function here. Now, instead of being this will be a traverse curry print block, uncurry print block on the fun blocks. So here, let's see. Label 1 has been removed, and the labels are visited in basically the order. 8 is now before 7, which kind of makes sense. Because we do branch 1, branch 2, yeah. But there was no merging to do, so this has just done the pruning, which is already pretty decent, but this has not tested the merging then. So let's try to figure out an example that would result in something being merged. Let's think about this. Can I come up with an example? Can I do something that results in 2 blocks being... Because an unconditional jump, we only insert an unconditional jump if we encounter a continue or a break. Not, or, aha. Or if I'm jumping to a loop. If I'm jumping into a loop, so if I'm jumping into a loop that creates a new block and I jump into, if the loop doesn't loop back and I can detect that, then we should be able to have a block that requires merging, which we can do. If I have if false return 42 or something, I'm very limited in what I can do at the moment given how many things I haven't implemented yet, followed by a while false return 0, something like this. Now, there's going to be a block inserted at the end of the if to jump either from the false condition or from the end of the if, and then this block will be translated into a jump block that goes into the loop condition, but the loop condition will not have a second parent because the loop body will never go back to the loop parent because it ends on an unconditional return. So if I run a previous version of the code that doesn't do the merge, there should be an empty block there that will be removed by the code we have just done. So first, let me remove the merge, basically. So if I comment this out, to always do this, which I block is unused, that's fine. Except that's a warning. And merge is defined but not used. Okay, that's a bit annoying. So if I run this example, I get this. Label 0, the start of the function is we assign false to the register 0, and we branch based on the value of the register 0 to either label 2 a positive case or label 1 negative case. Label 2 is the if block, and in which we do assign 42 to a register I1 and then return. Then 1 is the end block after the if. I probably would like to actually no, I always need to create the resume label first. That's why resume label is always 1, because if I have else if, those would be labeled 2, 3, 4, 5, 6, and 1 will always be the one that like closes the if. Anyway, label 1 here is the end of the if, and it is an unconditional jump to label 3. And label 3 is the condition of the loop, which for now just assigns false to the register B2, does the branch based on that register. And 4 is the loop body that does a return. And at the end here, label 5. How do we jump to 5? Oh, in the case where we don't do anything. Oh, this should be this should have been an error. This should have been an error and wasn't. Because here, I should have had an error about... Oh, but did I not implement that yet? I probably haven't implemented that yet. Let's go back to... There we go. This is this case. I end up with like, oh, there is no more instructions in this block, and there's nowhere to go to from here. Therefore, we do a return with no value, because that's what the end of a function is. This should emit an error, because this function here returns an int, and no return statement was provided here. But that emit error that I was surprised not to see is currently commented out because I don't have the reporting mechanism yet in this part of the code. So this makes sense. And so we have those labels. Now, if I put the simplification back, one of the blocks should go away. Label 1 should be merged with label 3 because there's only one jump to label 3. It is this one from label 1. So the label 1 ends in a jump, and label 3 had its destination has only one parent. So since they are directly linked from one to the next, they can be merged, and as a result, label 1 will be the loop condition, and label 3 will be gone from this if it works. So let's do that. Let's put this back. Okay, so we have label 0 the start, label 2, which is the if, label 1, which is now the loop condition, 4 and 5, label 3 is gone. So that worked. Now, not only do we prune unreachable blocks, we also merge blocks that do not need to exist anymore, so that there is no longer like a bunch, like indirections in blocks is now fixed. There is a lot of more. This is not. It doesn't even count as the optimization phase. There's so much more we could do, like detecting like false means this branch could be replaced by a jump because we always know where we go. Like this whole function could be replaced with one instruction. It could be replaced with like a return 0, whatever, because we know we can do static analysis on the thing. This is not the optimization phase. This is just the cleanup of this IR generation. Okay, so now that's done. Actually, oh, I didn't commit anything for 3 days. I should probably commit a few things. That's not what I meant to do. That's not what I meant to do. I meant to do that. I have to scroll this back so it's all visible on stream. There we go. So I'm gonna want to commit what I have at the moment. What has changed here? Symbol no longer exists. Yeah. Again, since for now I am not yet in a version where I can do like incremental work because I don't have a full pipeline yet. I am not yet being very strict about my commit messages. And the commits being incremental. So this is 3 days of work that's going to be introduce IR, which is not the best commit message. We will be a bit more strict about this when we start having something that actually works and we start iterating on it. Now, let's go back to the lowering. There's a few things we haven't done, and there's a few things that are now just that will not work. The main thing we haven't done is processing of the expressions. We've processed some of the expressions, but at the moment, looking up the name of something, like looking up a path expression, unimplemented. So if I were to try giving my function an argument x, which happens to be an int, and start doing putting things in there, that would just not work. Actually, do I want to model the... I probably want to model the arguments of the functions as registers in the first block, probably. Because that's where they come from. They flow through the function by being arguments to the first block. But I'm not going to do that just yet, I think. No, I should probably do that. So, that's part of the many things I have to do. Because now, basically, what is missing here is finishing translating expressions into a series of basic IR instructions. And the other thing that we're going to be missing is doing an assign, which is going to be very complicated. And I might do only a simplified version for today. And we're going to be missing the seal block function, which is there, which is basically, since our graph has cycles, there will be times where I will translate a block of instructions into, or a block of statements into instructions without having all of the parents of that block yet. For instance, a while condition block has two parents before the while and at the end of the while, or any block that does a continue. So all of those parents will need to be known to be able to do resolution of the static single assignment. So there is a bunch of subtleties that come with that are detailed in this research paper that I've been using. I've made a small change, which is I'm using block arguments rather than phi functions, but otherwise same logic. So I will want to have at the beginning here I will want to add arguments. Oh, this is going to be a tiny bit annoying in the sense that I am not currently in a block, and all of my functions targeting a current block have been made in a way that this module doesn't know about the details of the state, which means I cannot add arguments at this point. That is a tiny bit annoying, if funny. Okay. Actually, I could look at process block and make the assumption that process block always is in a because process block starts with the start block. Maybe I could do maybe I don't need to do that. Maybe I could always make the assumption. I could make the assumption that process block That solves my problem. Okay. For later, assumption to be documented. Process block must be called while already in a block. Which means go no longer needs to exist. And this entire function just becomes this. And that means whenever I do a process block or a go in this function, that becomes a process block. No, I can't do that. No, I can. It's perfectly fine. Okay. Same label and the statements. I am continuing in the same block. No, that's not correct. That's not correct. I don't need the label argument at all. It is, I think, yeah. There we go. That is now correct. I'm in a block. I can therefore process block. Otherwise, I'm at the end. Perfect. So that's correct. Now process block, where do I call it? I call it in a few places. I call it here. So now this needs a start block, start label. And here, that means I need a start block loop block label. And I need a start block of the if block label and a start block of the else block label. Any call to start to process must be done on a block that has been all calls to process block must be done on a block that has been started. Okay, that's done. And now at the top level here, I am in a block. I have started it. I can do append argument. And I will need to do so for each function argument. So for each, and I'm going to do this as usual, AST, where are you? Function info. So for each of the fun arguments of the fun type here, for each of them, which is a identifier, arg name, and an arg type, what do I do? I'll get the translated type. What's the name of the function again that I'm looking for? Translate type, unimplemented. So that's also something we're going to need to do. So translate the type from something that was part of the AST, something that was part of the type checking, into something that the IR understands. Archetype. Then we can create a register, which is going to be make register, and actually I'm just going to do it this way. There we go. And then we can append an argument, which is the register. Does that take any other argument? No, it doesn't. Which means I can rewrite this entire thing into no, actually, I need more things. This entire thing can be rewritten as append argument of make register of translate the type. And I will also need to register that register, if you allow me this phrasing. So I will change the... I can't do that. So I'm going to need the register here. I'm going to append the argument to the register. And I'm going to change the map of registers to insert something that says that in the start block, that name, the argument, which is the arg name, that name means that register. Okay, so that's done. Now we can move on to what should I do next? I should probably do the type translation because it's what prevents this from working at all at the moment. So let's look at our type. Our type. Where are you? There we go. So we are going to want to do something that takes a path info resolved, which is the output, which is what a type will be represented as in the output of the analysis phase. And we want to return in a IR type. We want to convert that, which is the complicated information used for type checking, into a much, much simpler type representation, which is all that we need for the purpose of code generation. Well, it's going to be a bit more complicated than that. So let's have a look. Path info. Yeah, because this could be a generic type with type arguments. So I'm also going to need to do type substitution there, probably. Or no, probably not. I think at this point all types will be concrete because everything will have been instantiated. So I can probably ignore that. Can I? Do I change the values in the type information? Probably not, actually. Do I need to do that here? Let's have a look at core. Or even maybe at instantiation. I have this substitute types function. Where is it used? Not in this file. It is used in context and in core, okay? Okay, for a field access expression, that makes sense. The return type of a function call, that makes sense. And in context. Hmm. That suggests that I never actually change. When I instantiate a function, I guess I could try. I could just print the result of the analysis. If I instantiate a function, I don't know if its type. Well, let's have a look. Let's try this. Let's change this file to instead have a struct foo of t that has a field x of type t, and then let's introduce foo of t, a function which takes an argument y, which is going to be a foo of t, and returns a t, and it does return y dot x. And then I'll have a function bar that will return an int, and that function will do return foo of a foo where the x is 42, so an int. So this will register the foo function as like, oh, it has been instantiated with int. Therefore, as part of the symbols of this module, we need to export the foo of int function. And I can check what the types are in the case of a generic function that has been instantiated. Rust format is unhappy because this is technically not a valid text file. That's annoying. Just gonna fix that. There we go. Can I make it bigger? Yeah. No, it's not. It's just big enough for this screen. Okay. So with this, I should now go back to my main file, and I should change. So the main is no longer going to work. It's going to crash miserably for many reasons. I should try, however, before all of that. Here, yeah, let's print symbols, basically. So this thing. This is not going to compile because this is completely wrong, unimplemented. Actually, no. This is going to be that. And this is going to have to be monadic. But for now, I'm just going to say that because I just want to compile and have a look at how the types are represented in the case of a generic function to see if I have to do any substitution at that point, or if I can assume that a symbol that has been instantiated no longer has any type argument and everything has been replaced properly. Process block. Process block never requires a label anymore because the start label will have been done before. So any call to process block now needs to not include the label. Okay, should be all. And this needs a do block. There we go. Okay. So let's have a look at what this outputs. It's going to crash miserably, which is fine. Because the thing that I'm interested in is... Okay, so the only exported thing, the only symbol out of this was foo. Does that make sense? Oh, I have two functions named foo. That's... Wait. That should have been an error. The fact that it wasn't... Oh, wait, no. Diagnostic. This is not the symbol. Diagnostic. Error multiple declaration of the name food. I can't read. Yeah, okay, perfect. This is perfectly fine. I'm gonna call this one main. And in fact, I'm gonna comment it out to have fewer things in this. Okay. So it crashed with not implemented yet as expected. But in the symbols that we have exported out of this module, we have bar, which is a function named bar. The function type, there's no type parameters, there are no arguments. It returns just a type, which is a built-in type name int with no type parameters. And the body is a return statement of a typed expression, which is not an L value, which is impure because it's a function call, the type of which is an int. And the value of it is a call expression. Okay, so all of this is fine. All of this is typed as int. There are no type arguments anywhere. That's fine. What I'm interested in is foo of int, the instantiated version of our generic function. What are the types in this? The fact that it's labeled foo of int suggests that its name so render name so its name contains the type arguments, which is fine. That makes sense. That's expected. This is a bit hard to read. I'm sorry. It's a lot of very like high contrast stuff. But this function is named foo, but its canonical name is main foo of int because it is the instantiated version. Its type, it has one parameter, the identifier t. It has one argument which is named y, which is given by value, which is a top level declaration, which is a main foo that doesn't have name parameters, but does have an argument of type int. Okay. So the name, okay. So that answers my question. The types will contain the type argument for, okay. Because yes, the name is canonical, and I am not instantiating the types differently per... Okay. So I can go back here. I know how to proceed from here. So here, this will contain the name of the type, which uniquely identifies it, points to where it's declared or where it's a built-in type or anything like this, and the type arguments. So I will need to perform type substitution on there. Let's have a look at how my substitute type function works. Given a hash map of identifier to path info resolved, which will be the path parameters here, and a path info resolved. Oh, but it is in my analysis monad. Oh, that is extremely annoying. But it doesn't need to be. Does it need to be path params? Can it just be in any monad, or can it just be even total at this point? Yeah, it is a perfectly happy total function. So here this is going to be from maybe report um, missing parameter error of, oops. Actually, is there a lookup def or something like this in hash map strict? Is there a lookup default? There we go. So I want a lookup default. The default is missing parameter error. The key is name and the map is mappings. And that is the result of this, where missing parameter error is this. Okay. And that's the case of type parameter. So if I end up finding a type parameter, I find its substitution. Otherwise, I traverse everything else. Okay, so now that's a basic function. It's not total, but it's no longer monadic. Hello, how are ya? Which means I can use it in other places without being tied to. But it still ties me to the analysis. That's a bit annoying. That's fine. That's fine. That's fine. I'm trying to avoid. I am trying to be clean about the way my inputs are structured. And here, what bothers me is from the lowering stage of the compiler, I am importing something that is defined in the analysis file and the analysis stage. I am importing the instantiation. That bothers me a tiny bit. It's not the end of the world. That suggests that maybe that function could be moved elsewhere to not be tied to a specific phase if it's used in more than one phase. Anyway, here what that means is when I want to translate a type, I'm first gonna look. So I'm gonna get path name and path parameters. So I'm gonna get a path info. And the main thing I want to do is a case on the path name. which I'm going to do on a new line, which is going to give me one of the possible names. Well, in this case, it's going to be a role, which tells me what kind of thing that is. Since it's a type, I can ignore a bunch of them. For instance, since this thing is a type, it will not be a let variable, it will not be a function argument or a function pointer. It should not be a placeholder. All of those make no sense in this context. The only thing it can be is either a built-in type or a top-level declaration. So let's handle all of those. So top-level declaration with a name, a built-in type with a name that uniquely identifies the type. And all of the others, I do not care what they are. Those are all impossible if there's no major error in the code. So all of those at this point can be an incorrect type error. Which will be defined as report an internal compiler error in the IR lowering phase and counted a value type role, a value role, a value kinded role in while expecting a type. An incorrect role, actually, because placeholders are typed. There we go. And I'm gonna also give as an argument the type info. This is gonna be the path here. There we go. So now we have a proper error in case this happens, but it should never happen. And now we can handle those keys. So now we have the name of a built-in type. We can look at... Actually, why do I use it? Why do I use a name for built-in type? Why do I use a name for built-in type? I don't need to do that, right? Maybe for... Is there any situation where I need to use a name? Is there any situation where I need to refer to a built-in type by name? Or by name being this, like, name thing? I don't think so. I might do the usual thing of stacking yet another thing on top of the thing I'm doing, but I think this can be improved. Let's have a look at the... Oops. Unimplemented. Unimplemented. Let's have a quick look at built-in. Because here is where I have the names that I use for the built-in types. But are those actually ever used anywhere? For instance, do I ever use the int name anywhere? No, I don't. That name is useless. Okay. So maybe I could instead... I could instead use something a lot simpler than that, which would also remove the possibility for, like, for built-in types to have type parameters, which is kind of absurd. Okay, so let's not do that. Let's simplify things. There is no need for those things to have a name. I do, however, need to have this because I need to be able to like map those identifiers to those things. That's fine. But I can have a built-in type kind of thing. Which is gonna have do I want to prefix them with built-in? How do I want to name this thing? It's gonna be very similar to some other enums I have in other places, but I want it to be different ever so slightly because it will encompass things that makes no sense in the context of like the IR lowering. So yeah, I think just built-in int, built-in character, built-in boolean, built-in unit, and built-in void. Which means I can go back to name and change built-in type to just being a built-in type. And that means built-in type here takes built-in int. And this takes built-in character, built-in boolean, built-in unit, and built-in void. Okay. That is a lot simpler. I might have... Do I have a core file for this one? No, I don't have a boot file. Do I have a boot file for name? I don't, I think. No, I think I don't. I will need to, because now this takes... This type must be... Ah, that's annoying. That is annoying, because now this creates a circular dependency between this file and this file, because a role now is aware of what a built-in type is. Ah, extremely annoying. That's fine. That's fine. Because I will just need to import a tie-breaking version of internal build, no, not internal, batteries built in. There we go. And that means I need to have built-in boot that just contains data built-in type. There we go. Let's see how this breaks. It's going to break a bunch of things because I've stacked yet another thing on top of something else. And this should be built in, and I'm going to take this and I'm going to put it in the boot file. There we go. Is it just instance show built-in type. I think it is. An instance EQ built-in type. Okay. This requires ORD as well. Okay, so I need ORD here as well. Do I need anything else? Generic for hashable. Okay. That means that built-in type is likely to require at least one of those. I think, yeah, hashable is what I need. Okay. Could make a derived yes, so I need generic here. I could implement it myself, but it's fine to do it this way. So I can then do an instance hashable name, like so. Okay. Duplicate instance. Oh, built-in type. Okay. Hopefully that's everything. Now that is a place I was expecting to find something that was an old name for a built-in type, despite the fact that, and now we no longer have that, so that is an issue. So that is generate full function name, so that's the thing that creates a canonical name for a function that was generic that is being instantiated. I know why I've made this. I have made this because the canonical name for something, the arguments are themselves name. They are something that points to something unique, which is the whole point of a name. This points to something unique, which means that built-in types must have a unique name as well. Okay. So I can revert some changes. I can revert that. I can revert that. I can revert that. I have to keep that. Okay. So that's why it was done this way. There was a reason. Which means I can go back to my lowering functions here. And here this is indeed a name, but since it's a built-in type, it has to be one of the already existing names. So I can match pretty explicitly. It will be a built-in name with an int name, and so on. So I will need to import batteries built in here as well, which I'm going to open here. Yeah, okay, I don't even need to have that. So I can do the basic one, character name, boolean name, unit name, and void name. So, and if I end up finding anything else, that's an invalid built-in type. Incorrect type error. Now the question is, what do I do in the case of unit? What do I do in the case of void? Because there's a few places where what I do is I assume that this function succeeds. Translate type, there's a few places where I use it. Here for a cast, for instance, I translate the type of the cast. I'm casting this as int, I'm casting this as enum, whatever it is. And I create a register out of this. In the case of cast, it should be fine because here it will always have been rejected as like I cast as unit, cast as void are things that make no sense. The type checker has already happened by that point. I know this cast is fine. There's a few places, however, where I might encounter a translate type that happens to be unit or void. In the return, and I guess the main place where this might happen is the return type of a function. Because a function that contains something that will panic will have a type labeled as void, which is a special case of a built-in function. And a function that does not return anything will be labeled as unit. Oh, that's not the only thing. Assignments will also be returning unit. What that means is I cannot translate the type of those into something because there will not be a register associated with them. Those make no sense. What that means is I'm thinking I'm going to do the same thing I've done earlier yesterday for something like this. I'm going to have a force type for the situations where I know for certain that a type must exist, which is going to be a very basic combination of translate type and then from maybe. And what we do on the case, or I'm going to write it as a classic thing, from maybe incorrect type error of translate type, where the incorrect type error will be reporting an internal compiler error encountered void or unit when looking for a register type. Type info will be, I'll need the path then. Up, there we go. Where here translate type will return a maybe so that I can handle the case of this gives me a thing that cannot be a register. So unit name, void name, nothing. Those cannot be registers. Built-in type int character boolean. Those are trivial. They are int boolean character. There we go. Okay. Next, so that's the basic types. And now we have to deal with the enum types, with the top level declarations. So something that was declared in user code. And that means there are two kinds that we might encounter, enums and structs. And this is going to be the complicated one. Oh, actually, this is going to have to be a monadic function. This will be in our lowering M monad. So will this. Which means this is an F map. This is pure. Because this case here is the case where we open a do block and we start doing lookups in the reader context. Okay. Because what we have is an interface which contains a definition cache, which is this, which means we'll be able to do lookups of the types that we find in the thing here and get the corresponding definition to see what kind of type they are. Okay, so I encounter a top-level declaration that has a given name. That means I can get its definition by doing, is it view? I never remember. Lens getter monad reader view indeed or view s. Okay. So I want to do a view, and on the interface I want to look at the interface definitions, and the function I want to apply is a lookup, because it's a hash map, of that name. Because if I remember correctly, the definition cache is by unique name. Yeah, perfect. So that gives me a with location definition if there is one. And crucially, on nothing, missing type declaration error. That means our function did not contain, that was not, we didn't try to do lower something with a full cache of the functions. That's incorrect. So IR lowering could not find definition for top level type. The type I need is, I'm trying to look up, is going to be given as an argument, and that's going to be the name here. So plus show name. Okay. So now I have the definition of the type, which means I can do a case of the definition. And I will get one of the many kinds of definitions. I'm actually gonna go back here, do that, put the AST back here. Definition. There we go. So here are the 4 possibilities, 5 possibilities. Type, alias, definition. Impossible, this would have been resolved. I should never encounter this one. So that's an incorrect definition error, I guess. Likewise, if I end up finding a function, I am looking for a type that is not correct. Likewise, if I end up finding a constant, I am looking for a type that's incorrect. I could do a catch-all for all of those things, but I'd much rather have a full explicit list, which means if I ever change any of those enums at any point, I don't have to worry about, like, is there a catch-all somewhere I have missed if I don't have a catch-all. And here are the ones I am actually interested in. I am interested in, and I'm going to put them last, actually, a struct definition. and a enum definition. The enum case is going to be the easiest. Oops, I didn't mean to do that. I meant to do that so that I can have the IR here as well. So this is type is what I'm trying to create. Let's have a look at enum info. There we go. So the way I represent an enum type as far as my IR is concerned is basically as an int with a bound with like a bound basically. So in the case of an enum and an enum info, that's very easy. The only thing I have to do is to return pure of. Oh, actually, function types are a thing for which I might have been a tiny bit too callous about saying like, no, functions don't make sense. Since I technically support function pointers, I will probably need to support functions and function types as well, which actually are incorrect. I have changed the way they are represented. This is correct. Okay. So no, actually, I'm going to have to handle built-in function. So those, yeah. How do I do this? Okay, I'm going to put the correct ones first. And I might have to handle function definition as well. So built-in function. But type built-in type, that's not one of the ones I have already handled. Should not make sense. Type parameter doesn't make sense. Placeholder doesn't make sense. Function pointer, however. Function pointer might make sense. I might have to handle this. Okay. I think I'm gonna introduce helper functions just to make the routing a bit more explicit. So handle so translate declaration of the name. Translate declaration is gonna be that. Okay. Introduce some new lines for readability. Okay, and how do I handle built-in functions and built function pointer? I don't know yet. I'll figure that out afterwards. For now, let's do top-level declaration. So I get the definition. I do a look at the definition. Maybe I'll need to do function definition as well. Yeah, actually, I will. I will need to do that. The register for a function type will just be an int, basically, in terms of like how my backend will implement it, but which is going to be the address for the function. Okay, so let's do the easy case first. I have an enum info. I can return the type of that. The corresponding IR type is an IR. No, type is missing here. It's an enum type. And the only thing I care about is the number of possible values. And that's just the length of the enum values of the info. Or just info, actually. Okay. That's enough to represent an enum. Now, I have a struct. What is a struct? It's going to be a list of fields, basically. So I have in a struct a list of values, and the type have not been... I'm going to need to do the type substitution there again. I'm going to need to do the type substitution there again. Ooh, that's tricky. Okay. So for translate declaration, I am the top level declaration. That means that the path might, for the case of a struct, there might be type arguments. Like the type I'm dealing with is this struct declared there that has a type argument with this type argument that was given to it. So I will need to do the type substitution there. Okay. So that means, so here, translate struct, I think, is what I'm going to do. I'm going to introduce a new function just to keep my case things a bit more readable. Translate struct, which will take the name. Do I need the name? No, I don't need the name. I just need the info. Translate struct takes as an argument the struct info and does first, I'm going to build the mapping from the type arguments to the actual value that was provided. So param mapping is going to be a hash map created from a list, which is going to be for each parameter name in the list of the struct params. I don't even need to do that. I can do a... Is that a zip? Wait. I have here the name of the parameters in order in the struct params. And in the path info, where are you? I have the arguments which are path info themselves. So instead, this is obtained by doing a monadic action, which is for each of the struct params, for each of a zip of the struct params and the path params, there we go, which gives me a pair parameter name, parameter type. For each of them, I perform a monadic action, which is a force type of that parameter type. Can I do that? Or can it be nothing? It can be nothing. Nothing prevents me. No, unit cannot be named by... Could it be possible for a user to create valid code that results in something having a type parameter of unit? I don't think so. because unit cannot be given as an argument to like type specialization. Hello, how are you? Made it home safe? So unit cannot be specified explicitly for type specialization, and no value of type unit can be created to be given as an argument to a function or something like this. So a type parameter will never be unit. Therefore, I will never encounter unit as a type argument to a function or a struct. Therefore, I can force the type because unit will never happen. Okay, so that gives me the IR type, translated type, and I return. I guess I can rewrite this differently. So I zip the two of them. That gives me a list of pairs. That gives me a list of pairs. If I traverse that list, I can apply a function on the pairs that returns something in the monadic context. If I traverse the list, I will be applying something within the pair, but will return something. And in the case of a pair, the rightmost, the second value is the one on which the function is applied. So this is a traverse of force type of this zip. This gives me a monadic list of pair argument name, parameter name, resolved parameter type, and I can do a map from list within the monad on that list of pairs. Okay, there we go. So that creates the parameter mapping, which means now if I go back to instantiation, substitute types. Oh, of course. It does the replacement before I do the translation. That makes a lot more sense. So that means that I need to start by doing the substitute types. Can I do it immediately, actually? Can I always do it on the name? Can I do it immediately on this path info resolved? I probably can. Because... But I need to know the mapping. And the mapping comes from... No, I cannot do that. I need... this is complicated. This is complicated. I can't do that there. Okay, what I'm doing is wrong. I'll fix that. So for each path parameter, okay, so that is more or less correct. That is more or less correct, but except it doesn't, I don't need to do the force type, nor this is required. The param mapping is much simpler than that. It is just this zip. This struct expects those type parameters, T, U, V, A, whatever they're called. And here are the values that were given for them that I know in this context are concrete types. Okay. That means, however, that whenever I encounter a field, I can do a substitute type, which is what I want to do, because what I want to do now is I want to create a list of types from the fields. So I go back to my struct info. The result that I want will be the result of applying struct type to, for each of the struct values, which is the field in the thing, I'll get a tuple, which is the identifier I don't care about, and the field type. And for each of those things, I will obtain the concrete field type by doing the substitute type thing using the parameter mapping we have just established. Okay. Yeah, that should be fine. This field type, that gives me the concrete type, and I just need to translate it again by doing a force type on that thing. So I just need to do that. Okay. And that should be enough for struct. Whew. Not easy. But now we're done with translating enum, struct, built-in types. Now, the only things we need to figure out is, do we need to do any translation for function types? And I think the answer is yes, because I can do function, I have function pointers in the language. Therefore, there will be values in some context that will be a function name, and I want that to be a register. So I need to be able to convert that into a function type. And that means both encountering a function definition as a top level declaration, I think, and encountering a function pointer or a built-in function. Although built-in function might not have, I will probably not want to allow function pointers to all of the built-in functions, because if I do, then I need to handle void as part of the return function types. It's fine, I can do it. Okay. So let's start with the function definition. Which will be translate function definition. Which therefore gets a function info. But in this case, this will always be a concrete function. So its name will be with int and everything. No, it will still contain things. Yeah, with parameters that are, yeah, okay. Okay, so no, the same thing still applies. So here I need to do two things. I need to figure out the type of the arguments and the type of the return type of the function. So the mapping will be very similar. Actually, can I use Ah, I don't have the full path. I don't know if an instantiated function in the case of an instantiated function, which this will have to be, I think there is no longer any type parameter in the path because the path has a name that contains the type parameters. So that means here the name contains the path. So here it's not. So here I need a name. Wait, no, it has been instantiated. The fact that the function has been instantiated means the arguments have been replaced. There is no longer any. There is no longer any need for. Yeah, at this point, I don't have any problem. Okay, so I don't need to do the mapping here for functions. Wait, but the function definition, however, does not. So I still need to do it. This is annoying. I guess. I guess I could look into the actual. Because that information is. Yeah, okay, no. The definition does not contain the parameter substitution. I have to redo that. I could do a second lookup of like, oh, this is a top level declaration. Is that a function? And go look into the generated symbols to get the already done thing, but that makes everything more complicated and more different. No, I'm just gonna have to redo a mapping, which is a tiny bit annoying, but not the end of the world. So here, that means that the function definition needs to know the name of the function because I need to know what that function was instantiated as if it happens to be um, if it happens to be a generic function. Okay, I'll get through this. And so here, this will be the name parameters for the function. Oops. Because the assumption here is anything that points to a function in the context of trying to get a function pointer points to an instantiated function. There is no such thing as pointing to a generic function. Therefore, the name will contain the parameters, which means I can zip function definition. Where are you? I can zip the fun params of the fun type with the name parameters. That gives me the mapping. And now I can look at my. I can look at the arguments and the return value and do the same kind of substitution. So that means that the arguments will be for each fun args do the same thing, ignore the name, get the field type, force the evaluation of the type by doing a substitution of the parameter mapping and the field type, arg type. That gives me the arguments. The return, the result is going to be obtained by doing the exact same thing for the function return type, which is a return type. There's no name. This is going to be, do the same thing. And the only thing is I'm going to do a maybe to list of that thing. Oh yeah, actually, that's, I don't even need to do a maybe to list. That's a maybe type because not all functions return something. And this is not a force type. This is a translate type because it is okay for it to fail. Wait, so I have a maybe thing. I'm doing a for and something that gives a maybe, so I'm going to end up with a maybe. Can I do something better there? Can I do something better there? Or I can just join it afterwards. That's fine. Because I could do a sequence, but nah, it's fine. Okay. So here I have done the same thing on the return type of the function. The result will be oh, here I need a just. And here I need a just as well. And so here at the end of this will be pure of just of a function type with the arguments and join of the result. Okay, so that's translating a function definition. That's almost all the cases I wanted to handle. I also need to handle the case of built-in function and function pointer. Built-in function I might not do yet, just because I don't have built-in functions yet. So built-in function is just a name, but I have no information about that function anywhere. So I think for now, built-in function, impossible. Unimplemented. I have a function pointer I could have, and that just contains a function type, which by definition will be already resolved, so no need to do any mapping. So that's convenient. Which means I could rewrite this as being translate function type, which takes the mapping, parameter mapping as an argument. Because everything I need, the arguments and the return and everything, this is all in the function type. Yeah. Okay, so I only need here the function type as an argument, which means, yeah, fun args, fun return, that's all I need. Which means translate a function definition is just calling translate function type with the parameter mapping, which is this thing, and the fun type. And translate function type is this and does that. And I can use it here for the case of a function pointer, because here I have the function type. Actually, it's going to be a conflict, so I should name it info or something. And here I can do a translate function type. Of a empty mapping, because here it's impossible for it to still contain type parameters and the info. There we go. Okay, so the only unimplemented thing we have is built-in functions, just because we don't have any at the moment, so I have no idea how I'm going to translate their types when I don't have their types at the moment. So now that should be all for translate type. Took a while to write, but that's a big thing out of the way. Let's try to make it compile and see if there's anything broken about this. Oops, this is slightly too big to fit on the screen. A name is not an argument here. So I should give it here. Oh, there's a few places where substitute types was monadic and no longer is. This is going to be a bit of an issue. So this is info on which I modify path params by doing substitute type mappings. Wait, no, that's completely wrong, is it? No, it should be fine. Ah, no, okay. And I need to traverse that, I think. Or is it, no, it is just that I want to do a map here. Yeah. Without the dot. Okay. And here, this is a place where I expect this to be monadic, and it's not, so this needs to be put into the monadic context. There's going to be a few such errors in the thing. Like here. This is no longer monadic. Like here. This is no longer monadic. Those functions are, at this resolution, are unreadable. Aha, yes, of course. That's annoying. Okay, so I'm back in this at this point. So I will probably want to only import the things that I need from this, because otherwise I'm going to have a few issues. Or I could be explicit. Type. This is going to be an IR build type. Yeah, I can just do it that way. Okay, hopefully that's enough. top level declaration, and all of those are things that come from role, which is not imported in this, and it is part of the name module. There you go. Ambiguous occurrence function type. Yep. So that's an AST function type, which I want to differentiate from an IR function type. Scope info. Yes, it's called info lowercase. Oh, length. There we go. Incorrect definition error. Not in scope. Yes. Incorrect definition error. Encountered an incorrect definition while translating a type. And the definition I got is this one. Here, translate type is no longer correct. When I do a register here, this is a function argument. It cannot be unit or void. It has to be a translatable type, force type. This is a function archetype. Oh, yes, of course. That is a function archetype. Wait, I already have a function for this. I already have a function for this. Archetype. Somewhere in there. Yep, there we go. This is the function archetype. Which I'm going to rename arginfo just to be clear, because this also contains information about whether it's by reference or by value. So I need to get the function archetype out to then be able to call force type to get the IR type of the thing, to be able to call make register to know what kind of register to register, and that gives me the register that I can put in the arguments of the first block. There we go. Okay. Function archetype. It helps if I name it correctly. Zip not found? No. Oh no, okay. Oh yes, of course. This the zip is not accurate. This is a from list of that. So here I'm making a register. This is for a cast. I cannot cast to unit or void. This is force type, not translate type. Here, translate declaration. Translate declaration gives me a non-maybe type. Interesting. Yep, I forgot to put the just here. Those definitions are annotated with the location, so I want the actual thing within. And for readability, I'm also gonna introduce a translate enum that takes an enum info and just does that and nothing else. But that way, translate enum def info. It is symmetric with, well, symmetric isn't the right word. It is similar to the other ones. Located is not in scope. That means I need to import representation location. Ideally without any typo. Info is not in scope, but the enum name, oh, it's enum values actually, so completely wrong. Okay. And there's a place I've seen a non-empty and list. Which one is the non-empty? I guess, yeah, I guess my structs cannot be empty. Therefore, their list of fields is represented as a non-empty list. Therefore, I should probably represent here this thing as a non-empty list of type. Okay. We're getting close. Prior mapping is still wrong. That's because it is not a list. It is a map from a list of the zip. I'm just going to do the same thing here, and I'm going to reintroduce for readability. Up, there we go. What else am I forgetting? I'm even tempted to do that on tubes. 2 lines. Like so. I think that's better. Okay, so now this is supposed to be a map from identifier to path info resolved, but the fun type, the name parameters, are those a name? That doesn't work. Oh, that is frustrating. Okay. That is frustrating. So the problem I have here is I need to know the exact concrete type of this function. This is where a function appears in an expression, therefore a function pointer appears in an expression, and I need to know, I want to represent that type in, I want to capture that type in my IR so I can do some shenanigans later. In the code generation, I will need to know the type of a function that is being called. So if a function is being stored in a register, I want to have the type associated with it. That function could be generic, is the problem. So I found that, oh, the thing I'm looking at that happens to be a function, its declaration was here in the code at module main at line 36, whatever. That definition, the types of the return type of the arguments could be generic arguments because functions can be generic. I know that the function I'm pointing to is not its definition, it is the instantiated version that has a concrete type for everything. However, the definition is not overridden. Oh, unless I do. I could do that, I guess. I could override. I could override the definition of a function by its resolved version. I should do that. That would make a lot of things simpler. The question is, do I already do that? When I instantiate a generic function, I put it in the symbols. But I don't put it in the definitions, I think. Maybe I should actually, since they have a different name, I could... Oh, in fact... In fact... In fact... here, when I do a, let's look at the definition of the things I have access to and I look for the name, this will not work for a generic function that has been instantiated because this name will be the name of the instantiated function, not the name of its original generic definition. So I think the solution to both of my problems rests in making sure that the definitions contain the instantiated version of functions. So I will have a definition for the function foo without its subarguments, which is a generic function, and I will have a cached version of the definition for foo of int, the definition for foo of character, and so on. This means that if I go back to the analysis module, there's a bunch of things that are wrong about this. But the definitions, the module definitions here, okay. Where do I ever set the module definitions? Oh. Wait. Definition cache, that is indeed a definition resolved. So where do those come from? If I never set them anywhere, because I start them as empty. Am I never setting them anywhere? That seems wrong. Oh, wait, no. Here. So in core. That makes sense. Okay, yeah. So here, when I am done with looking at a definition, I add it to the list of the exported definition. That makes a lot of sense. What I need to do now is when I also do at the end of this, I instantiate all of the generic functions, which happens either with an explicit call to instantiate generic function or with a try instantiate generic function when it's available. In that case, I need to module declarations. I need to insert as well. There is no reason to only do it for non-generic functions. I will need to do that. And the symbol is just, it is just the function definition, but I need to keep the location because the location cache has a definition. So this will be symbol put in the, actually is it a functor? It is. So the symbol put in the located definition, overriding the definition by its resolved version. Okay. So with that done, now the result of doing the analysis, the type checking and name checking of a module will also contain a declaration for instantiated generic functions in which the types have been resolved. Which means that back in here, when I do this lookup of the definitions, I will get not the original definition that still has generic parameters. I will get the instantiated version, which means that when I translate the function definition here, the function info will contain concrete type information. I don't need to do the type substitution anymore. So this is always what I do. There's no parameter mapping. There's no need for that. So substitute types is not required. This is purely a matter of archetype. So this is just purely a traverse of a traverse of force type on the fun arguments. The result is a simple traverse of force type on the function return. Which I guess, nah, it's fine, like this. And the result is that. And that should be a lot simpler. Am I misremembering again the type of this? No, okay, so it is value on the left and thing. Okay. Oh, of course, the thing I have is a function info, and a function info is not correct. What I need is a definition, so this needs to be a function definition of that symbol. Almost. Wait, so this is a located definition, which is a with location of something. That is a functor. So I should be able to replace it with this function definition of the symbol. Is the symbol correct? This is part of the interface. Actually, let's go look at the monad definition for the analysis. Let's look at module symbols. Symbols is a symbol cache, which is a hash map from name to function info. And I want to make this as a with location definition resolved. So my function info, I need to put into a function def to get a definition, and I need to put that in a with location. Function def is the constructor to make that a definition that I put within this with location. What is happening? So the actual type is definition resolved, that's correct. I don't understand. This thing should have type with location definition resolved. If that's not the case, I don't know why. Doing so, splitting it means, okay. For some reason, it expects a maybe. It expects a maybe, and that confuses me. Oh, is it because the analysis monad? Yeah. That it is indeed a maybe there. Why do I have that as a maybe? I think that is because I use this to indicate both that I have finished, I have it, or that I know it will exist but I don't have it yet. Something like that. Okay, so let's look at context and let's look at core. Okay, that's only use, and in core, I'm not sure I understand what that means. Why do I have two layers of maybe there? What does this bring me? Why do I have that? I suspect I wanted to use it as a cache to indicate, but I'm not using it for that anymore. I probably don't need that. Oh, wait, is that something to do? Is that has something to do with the top level analysis thing? Oh, sorry, in core. The analysis is definitely the part I've struggled on the most in this project. It is the most complicated part of the code and the one with the least readable code, I think. So resolve definition is a maybe. Because some things don't result in a definition, I suppose? I really don't understand why I have. I know. I know why. I know why I have a maybe. That will need some documentation. The reason why is I am using this I am using this cache as a record of the things I have already processed. So if a value is in the hash map, it means it has been processed, which means I don't attempt to process it again if you're like, oh, I should try to see what it's like. And I avoid doing the same processing multiple times. However, sometimes users make mistake and the code is wrong. So if a function has already been processed but written an error, I want to record the fact that it has been processed without actually storing a value because I could not create a value because there were errors in the function. Hence the maybe in the cache. That's why. So when I successfully perform the analysis, the instantiation of a generic function, and I have succeeded, then what I want to insert is indeed just of that. Mystery solved. I really need more documentation in the analysis. It is the worst part of this project so far, by far. Okay. Now, with this done, translate function type no longer requires the mapping. There is no longer any mapping. Oh, why do I give the name? I probably don't need to give the name anymore. That's also good. Ah, I have the same problem here that I have before, which is I can't just do a force type. This is gonna have to be a function arg type of this. Okay, so that's becoming a bit less readable. So this is a traverse traverse. The function is this. The value is that. The result. I'm not gonna keep this annotation. And here, as a result, I need to discard. I can do it here actually. That's going to make everything a tiny bit simpler. So this on a normal traverse. After I've made I extracted. I can do it here. Up, there we go. So I iterate over the function argument. I take the second element of the pair, which is the type. I get the actual underlying type, discarding reference value information, and I translate it into a type. And I might even be able to fit that into one line. Yeah, that fits into one line. That's fine. Okay, and that's the arguments. And I might want to actually do that here. Okay, and that's a maybe. Wait. Yes, no, that's correct. That's not a force type, that's a translate type. Because this is a place where I can get void or unit, and I want to handle them. And this compiles. Okay. It's going to be difficult to test immediately, but at the very least, I can try. If I comment this nonsense out, if I look at my current main that has those things, this should contain two symbols. It should contain bar, and it should contain the instantiated version of foo where t is int. Let's see. The problem is I'm doing lookups that I can't do yet. I am doing struct expressions that I can't do yet. So this is going to be a not implemented yet immediately. Not implemented yet. Yeah, there we go. Crashes immediately. So if I remove all of that nonsense and I go back to this function that I know will compile. Okay. And here, if I do something like this, x is an int, and y is a foo, and foo is... Actually, let's even try foo of character, where there's a struct foo that contains a field p that happens to be this t argument here, and there's a type alias of bar of t, which is foo of t. Let's go even further. Let's do that. And this thing has two fields, and this one is p1, p2, and this one is the second type parameter. Okay. And here, this is a bar of character. This should... It's not going to work on the first try, but we should have all the code required for this to be translated into corresponding stuff. That's because I am missing a semicolon here. Undefined. Undefined. Where do I have an undefined, actually? Here. Yes, okay. That makes sense. This is ugly as sin. This is my debugging thing for rendering the thing as labels here. I've just said that the registers are displayed, and I'm just not actually going to do that. I'm just going to do that. Which is good. It means we arrive at the point where we're trying to render the registers. That's good. So here, this function, main, the first label 0 has two registers, 0 and 1, which are the two arguments. Yeah, that seems to be working. I would like to know their actual types. I'm going to change this to actually show the types. So this is extremely temporary code. But let's do that. The enum type will be... so it's just going to be E, that's fine. For a struct type, how am I going to render a struct type? There's going to be a non-empty list of types. I'm going to render that as S, open bracket, plus something, plus close bracket. And the value here is going to be a intercalate with a comma, a map show, it's going to have to be an F map, I think, of the fields. Okay. And a function type, I am going to leave undefined. Okay. Oh, actually, no. Because we can probably already try function pointers. So this is going to be a function type, and it's going to have the args and the return type, and it's going to be rendered as being a function that does that kind of nonsense as well. This is extremely temporary debug code that should not exist, but is here purely for debugging live here. And then we are going to add another thing, which is the return type. So that's also going to be an fmap. I'm going to do it as plus show of maybe to list. Actually, I can do something a lot simpler. I can replace this as being a show of to list of the fields, and I will have the brackets and everything. But we'll have spaces, and I don't want spaces. That's fine. Okay. And I can do the same thing here. This is show to list of the arguments plus show maybe to list of the return type. Okay. That's absolutely horrible debug code. Because I want to see how the types of the arguments have been translated in the thing. Wait, why do I have only one function main? Oh, that's correct, yeah. Okay. So this translated as this register 0 is an int, which is the first argument x here, and the second one is register 1 containing a struct whose first field is a character, second field is a character, which is correct because this is a type alias giving character to something that then forwards to foo. Yeah, okay, so that seems to be working. So the thing we wrote with all the structure thing is now working. Okay. That means I want to try something else. I want to try a function foo that is generic. And it takes an argument which is of that generic type, returns that generic type. I cannot. I don't have enough. Let's say it returns an int, and the argument is ignored, and it just does a return 42 or something, because I don't have yet the ability to say x here for the purpose of the lowering to AR. Now, there is now a generic function in the module. I am gonna here. I don't have function calls yet. I wanted to try to instantiate it, so I could have an instantiated generic function and try a yeah, I don't have it yet. However, I can still try. Let's see what a function like this takes a z, which is a boolean, and returns a character or something, which will contain nothing for now. That's fine. I have done let statements, so I think let g equals foo. This should create a function pointer, and g should be a register that contains a function pointer. Nope, not implemented yet. There's something that we have encountered that I haven't implemented. That is at line 295. Ah, yeah, I haven't done any path expressions yet. Wait, I haven't done... Ah, yeah, I suppose it's not a constant. It is a path expression. The type is known, but it's not replaced by a function pointer at that stage. Interesting. Because it did compile. That means that I did recognize that the type of this let variable in my type checking will be properly recognized as function pointer. However, since here I am trying to then, yeah, I don't have this part, then I cannot yet. Can't I do that yet? Do I need to keep the path? Hmm. I will need, okay. I will need a new, I will need the new AR instruction. I will need something that gets the address of something else. Like address of the function. I will need an instruction for this. I don't have an instruction for this yet. Okay, well, that's still some of the work. It's still progress. We've done struct types and everything, and translate type seems to be working. Which means it's time to move on to the next thing. What do we do next? It might be a good idea to just do struct expressions. That's going to be fairly easy. Because path expressions are going to be the most complicated. That's going to require sealing stuff and everything. There's going to be this is where all the complexity of the research paper comes in. So let's try to do some easier things for now. A struct expression should not be monstrous. Famous last words. Struct expression. That's something that contains the type of the struct and the list of the fields. I don't care about the type at that point. Because if I encounter a struct expression, I already have done the type checking. That's just a matter of putting all of those fields on the stack, basically. So yeah, that should be fine. There's something I will need to do at some point as well, is I will need to handle panics. The translate expression thing will need to have a way of short-circuiting. So like, we encounter the panic. There is no need to add more instructions to this. This will have already panicked. Let's go and signal to the calling thing so that the calling thing can be like, oh, this thing panicked, therefore this code there below is unreachable. But we don't do that yet. We don't have panics yet. Let's not do it just yet. Okay, so let's do a struct expression. We get a type, I don't care about, and the fields. What do we do for that? Well, we are gonna want to do... It's all gonna be in the current block. There's no need to... Why do I have force expression again? Yeah, because all of them are supposed to read in the register. That's the case here as well. So this can be forced. So this is going to be the registers I'm going to obtain by doing for each of the fields, which gives me an identifier I don't care about, and an expression E. I will simply force the expression E, which adds all of the instructions required to compute the current value in the current block. So does the lowering into IR of every single field, and each of them gives me a register, which is where the value is stored. And as a result, registers will be the list of such registers. And nope. I have a special instruction at the end for combine. So I just need to... no, I do need to type. Because I will need to know... I will need to... The target will be making a register whose type is gonna be a force type from the struct type. And then I will output a simple... I will input one basic instruction. So I will append an instruction to my block, which is going to be combine into this register, this list of registers. Okay, so that's handling a struct expression. That wasn't too complicated. Array, index, not implemented yet. I don't have those. Field access, I should probably do. That should not be too monstrous. Famous last words there again. A field access expression will be I have the typed expression on the left. So that's the struct expression. And I have the field name on the right. What do I do there? Well, that's a struct expression, so it must be created. It doesn't exist ex nihilo. It's either like a struct expression directly, or it's a function call. Like something needs to happen. Instructions need to be executed for that value to exist. So I get the struct register by doing a force expression that it is supposed to give me a value. It's not supposed to fail. Can only fail in a panic, and we don't handle those yet. So I need a force expression there. On the struct expression. Okay, so add the instructions that create the struct in the first place. Give me the register in which that entire struct is stored. And I will then need to translate... No, I don't need to do that. I just need to get the type information from the struct because I need to know what index that field is. So there's going to be a get field index from the expression type of the struct expression and the field name. That will give me the field index. And then I will just append an instruction to my list of instructions, which is a get field. Oh, I need to target. Aha. So I will need the field type as well. So I will need to get field info, which is going to give me the field index and the field type. From this, I can force type the field type and translate that into something that the IR understands, make a register for the target, and then happen an instruction, which is going to be a get field, where we put in this register there the value which is currently in the struct register at that field index. Okay. So now we need to write get field info. Which is going to take, as we've established, the expression type and the field name. So we're going to do very similar things what we've been doing here. We are going to get a struct definition. This is a tiny bit annoying. This is a tiny bit annoying in the sense of like, since my struct expression is representing the type in the most generic way possible, I have to redo all of that logic to be like, hey, no, I need to find what the type of this thing is. And a lot of them would be errors. Okay, that's annoying, but I'm just gonna have to redo this. I'm gonna have to redo this, basically, as a new function. I'm gonna need to do retrieve struct info from a generic type information. This is going to give me a struct info resolved. So here, the only thing that is valid is for this to be a top-level declaration. Structs are all top-level declarations. There are no built-in structs. So anything else, incorrect type error. Then I need to translate the declaration. I might do this all in line actually, just because this is going to be a lot simpler. Here I can really just be aggressively, no, I need a struct basically. So I can get the definition from the surrounding reader context. If it doesn't exist, report an error. Now I have a definition. And I can do a case here. If it is a struct definition, perfect, return that. If it is literally anything else, something that went wrong, and that's an incorrect definition error. Up. This is not very elegant, but, you know, it works. So incorrect type error no longer exists, I think. It's an incorrect struct error. Retrieving struct info. Okay. Incorrect definition error. Incorrect definition while retrieving a struct info. And missing struct declaration error. Could not find definition for... actually, I'm gonna keep this one. Okay. That's ugly, but that's done. And now we can go back to translate no. Get field info. There we go. So I can get a struct info by doing this retrieve struct info that requires only the path info, which will crash miserably if anything went wrong. And now what we need to do is find the index of that field name. And I'm sure I have things that do that somewhere. Would it be a find index? Nope. No, it's not that. I know I have a place where I do that, but it's for enums, that's different. Okay. Do non-empty. Does non-empty have any like find function? It doesn't. Is find generic on any foldable? It is. Okay, so I will want to do... I will want to get... Oh, I want the index, actually. Yeah, I want the element in... Find index, there we go. Well, I don't want find index, I want actually to get both the index and the value. I'm just gonna do it myself. So it's gonna be a and I'm gonna make that a separate function then. So get field info is gonna become this. And I'm gonna call it retrieve field info. It's gonna take the path info resolved. An identifier. And return that, except it will be returning instead the tuple of index and type. So I will start with this. here being this case here. So now I have the struct info. And what I do afterwards is I do a go on the toList. Sorry, let me check. This is important. Nope. Go on a toList of the struct values, where go is going to be this function that on an empty list reports an error. Actually, I'm just going to make it a field not found error. I'm going to make it an error like this, just for readability. Field not found in struct definition. And the error messages we're going to add here are going to be field name, and that's going to be show the field name, and struct info, and that's going to take the struct info as argument. Okay. And otherwise, if we have a field that is a name and a type, if the followed by the rest of the list, if the field name is the one we are looking for, then this function returns index. That's not a thing. It's an int. And we go with 0. And we go here with I. And we return I, the index, and the field type, which is ft. And otherwise, if we didn't find it yet, go recursively with I plus 1 on the rest of the list. A very ugly manual search, but just because there's no function that gives me both the index and the value for a find, or at least none that I could find after a cursory search. Okay, so now I have this horrible retrieve field info, which gives me the int and the type, which means that a field access expression, I add the instructions that create the struct in the first place, whether it's calling a function, creating it, anything. I do this translation of the field info, so I know what index that field is within the struct's memory layout. I know what type the field is. I create a register that stores the value that we're going to extract. And I append an instruction, which is a get field in a target register from the struct register at the field index. Let's compile that. Identifier. It's not in scope. I have not used identifiers yet. Interesting. I probably have, but without actually naming them. Get field info is now called retrieve field info. is applied to one value argument. So there's something here where I already have. Oh, that's because I'm in a case on the expression type of the thing. Oh, this is annoying. I shadow the thing. Okay. Okay. In this case, I can probably do that. Okay. Combine target registers, expected register, actual non-empty registers. I suppose that's correct. Structs cannot be empty, therefore the combine instruction cannot take an empty list of registers. Therefore, I should change my combine instruction to take a non-empty list of registers. Okay. Yeah, this is not monadic anymore. What is wrong here? Because here I am not passing the argument to this thing. This is the struct info that I got here. So I'm just actually not gonna do that, and I'm gonna instead do that struct info. That means that Go needs to be aware of the struct info. Yeah, it's fine. It's fine. It's not my best code by far. Okay. Define but not used, that is correct. Okay, and there we go. So now we should have struct expressions and field access expressions, which means even though we don't have a lot of things, I could be trying this, something like this next. I could make a new struct, unique, that contains parameterized by a field t that contains one that happens to be a value of type t. And here I could do something like this function foo, so that doesn't work here, I have to remove it. I can make it so that it creates a struct expression by creating a unique value of type unique, by giving it one value, which is going to be the character star. So struct expression should work, and field expression should work as well. So dot one should return something, and I can do a return of that here. So that should work. Okay. That feels. Uh, yes, it works. I was expecting to see the instructions for creating the struct and then for getting the field, but creating the struct and getting the field, this is all constant. Therefore, the optimizer has kicked in. Well, the optimizer, the very basic constant unfolding optimization, and this has been replaced by return star. Basically, we don't construct a struct just to remove a field. So this works. Okay, so I am gonna change that to be foo1 and foo2. And foo2 is going to take an argument which is going to be the struct, which is going to be a unique of character, and do return of s of 1. And foo1 is going to do, I can't do function calls, I don't have function calls handled yet. I can do this returns a unique of character thing, and it creates it here by doing 1 equals star or something like this. So now I should be able to test both struct creation and field. Nope, that's not gonna work because I don't. The lookup of the S is not gonna work yet. Okay. But this one should work. Nope, because wrong syntax. Okay, this one does put star in a register, combines into a register that is a struct that contains only a character. I could probably do something smart, but I will let the code generation do that. Of like a struct of only one field can be replaced by that one field, basically. But that's adding more complexity to something that's already complex. Let's not bother now. That being said, this would make a lot of things easier because suddenly I wouldn't have to do get field, set field, and a bunch of things. I might want to do that as part of the optimization phase, probably. Okay. Yep, that looks correct here at least. Okay, so this nonsense works. We can move on. Range unimplemented, that's fine. Call, so I think the big ones, I'm gonna make a list of the ones that are not implemented yet. Range not implemented because I haven't done arrays yet. So array expression, index expression, not handled yet either. This will come later. So I think now the two difficult ones that I haven't done yet, and because I've done everything else, I think, except assign. Assign hasn't been done yet either. Well, it's been partially done, are path expression and call expression. So a path expression is going to be, here's a name, X, for instance. We need to figure out what that thing is. And if it is something that is local to the function, we need to check which register it will be coming from. And this is where some of the complexity comes from. Because this is where we do the recursion that is described in the research paper, where let's go back to the research paper. So I am in the while loop, the while header, for instance, where I have a while x is different from 0. What is that x? X is not defined in the here, so it is probably defined above, on the entry loop, like on the code before, let x equals 0 something, or like let x equal 1, and it is also probably modified in the loop body, which means I need to look to know what register to read to get that value. If it's not defined in my block, it's fine. I just call the parent block. It's fine. But if there's more than one parent, then I need to ask both of them. And I need to, if there's more than one answer, there's more than one kind of register that contains the value, then I will need to, what this paper does is a phi function. What I'm going to be doing is a block argument. Make this an argument to the block. That value, the register that will be, in which the value will be stored, will be given as an argument. This is where things get very complicated, because it means doing lookup recursively through the parent blocks. It means if I discover that the thing needs to be a phi function block argument, I need to register the argument and I need to modify the calling. I need to modify the terminator calls of the parents to include that argument now. And I will need to handle the fact that at some point I will be processing blocks whose parents have not been processed because there are cycles in the graph, which is what is described in this part of the research paper. Where is it? Oh, it's actually this one, on how to handle incomplete control flow graphs. So that's where all of the complexity comes from. It is a nightmare. Which is why I'm going to start with functions, I think. I think functions are going to be a bit easier, which is same something. So call expression. That is a path info. So it's something that points to a function. It could be a local variable. It could be a local variable because I support function pointers in this thing. So what we're going to need to do for a function call is create all of the expressions for the values on top of the expressions, as in for this thing, what's the register, like create registers for every single thing. Then I need to do a lookup of the function to decide whether it is something that needs to be in a register or if it is something that is just a name, an external name, something that will be linked later that I don't need to know the address of at this point because the linker will care about it. And then I need to insert the corresponding call to the function using one of the call atomic instructions. And I need to maybe store the register if the function doesn't return a unit. That is a lot. That is a lot of work. And it's getting late. On one hand, I would really like to finish this because now this is the nitty-gritty of the complicated part of the research paper, but we are so close to have most of the basic functionalities of the language implemented in the IR. That means next week we could start doing the code generation almost. Yeah, I'm gonna take a 5 minutes break. I'm gonna get a drink. And I'll tackle at least function calls. Yeah, that's empty. Be right back. Okay, let's do this. So, a call expression. I have the function path, and I have the call arguments. So first, I'm going to need to retrieve the function information. What will I need there? I will need the actual function type. I don't think I need more than that. However, if this is actually a thing that points to a local function variable, because again, I have function pointers, then this should not give me so it should give me the function type, but it should also give me either the function name, the unique name that uniquely identifies the function that the linker will be able to resolve, or the register in which the function is. So that gives me, the function type and the function name is not correct. Value, let's say. So I'm retrieve function info from the function path. Then I thought I had call instructions. Where are they? Oh, invoke. Yes, there we go. So I will need to know what the return type of that thing is. And this will be a translate type, but only a translate, not a force, because some functions will return either void or unit that do not go into a register. So that's going to be a translate type of the fun return of the function type. That is not entirely accurate. This is a maybe. So I'm going to traverse with translate type. That gives me a maybe type if there was a return type and it happens to be something that we can translate. So that's the register type. Well, yes, that's the register type. That's a maybe register type. So the target register will be traverse of make register of join of the register type. So we combine those two maybes into one, and we traverse to make a register only if there is actually a type. Now we have the target register. This is where the result of the invocation of the function will go. This is probably the one we want to do last. So instead, I think the first thing we want to put on the stack is the arguments. So for this, I need to get the registers. So this is going to be a traverse there again of force expression of the call arguments. That gives me the register in which each argument is gonna be stored. Then now I have the register type. I have the register for the arguments. I have the register for the result. I can emit one instruction, the type of which will depend on the type of function I get. So I will append an instruction, and based on the register, the function type, sorry, the function value, I suppose. And if I get, let's say that left is for register, so if I get a register, then that becomes an invoke from a register with this target. I'm just gonna say target. I've used target everywhere else. And this register and those arguments. And if instead I have the common case, which is I have a function name that the linker will resolve later, then that's an invoke of a name, and that's with the same target, name and arguments. So that's the basic thing done. Now we need to do this function info retrieve function info function, which is going to be based on the same logic as this retrieve field info. So I have a path info, and I want to obtain a function type. So I want a function type resolved, and I want here either a register or a name. So let's do something very similar to this, I suppose, which is, I copy all of that, errors included. Let's have a look at what the path is. And there will be more than one possible case here, because a function call can again either be a local variable that happens to be a function pointer, or an actual existing function that we can link against. So here, let's be explicit. Let's handle all of the cases. So if we find that the function that we're trying to call points to a top level declaration, that's great. That is one that is defined at the top level. That's perfectly fine. So we have the name that uniquely identifies it, which is the thing that we're going to return here. That's the thing that the linker will link against. But we still need to do a translate of the declaration because we need to extract the function info. If we get a built-in type, it doesn't matter what built-in type we get. Oh, wait, it's weird that I've done this. I'm going to fix this here. The catch-all is going to be with, yeah, there we go. Built-in type, that makes no sense. There's no built-in type that can be a function. Type parameter should never happen. Placeholder should never happen. Function argument cannot happen at the moment because I don't have a syntax for a function argument to be a function pointer. So at the moment, that's not a thing. At some point, it will be. I want to have syntax to be able to do function passing and that kind of stuff. So at some point, there will be function arguments as a possible location for a function to be called, but not yet. Wait. Oh yes, it's because I've copied two different things. Okay. So I'm just gonna remove this. And just do that. I don't need to do that. So if I find a top level declaration, that's perfect. If I find a function pointer, I don't know how I would find this. I would find this, I suppose, if I have resolved I don't know if this can happen. When do I create a function pointer? context is the only place I create function pointers. So that's when I'm resolving an expression value. But the type, yes, okay. But it will be a path expression. Okay, so it cannot happen because that's a type information. And here I am looking at some kind of value that I'm trying to call, and that function pointer would be type information that is nonsensical here. This cannot happen. So, incorrect type error. So, top level declaration, we are trying to call a function that was declared somewhere that I can link against. Built-in function, I'm trying to call a built-in function. I haven't made anything for those, so this is still unimplemented, but that's valid. And function argument and let variable are the other ones. That's going to be unimplemented for now. I haven't done the work required to have function arguments as that are function pointers, but a let variable that is valid. This could be a valid function. So, what is a let variable again? This is as part of name. It's in role. It's an identifier. Okay. I'm gonna call that name as well, even though it's a bit different. And that's the function type. Aha. And there the type will probably, it is a path info resolved, but the type is all likely to be a function pointer. Okay. Which means I'm almost tempted. No, I need the name. I come to that. Okay. So this here, I will have to translate handle variable name fun type. Okay, so those are the two cases we have to handle. Incorrect type error. Encounter an encounter when retrieving function info. So now we want to do translate declaration, which takes. I'm gonna do the same thing we have here. It's that basically. I get the definition, declaration definition. I use the two terms kind of interchangeably. Let's retrieve the definition of that function from the reader context. If it's missing, we fail with missing function declaration. That's an internal compiler error, something went wrong with the cache. Then we look at the definition, and if it's anything but a function definition, then we fail with an incorrect definition error. Okay, and now we can do translate function type. Maybe don't translate. Handle. I'm not in a translation function. So, handle function type. Actually, I don't need to do that. This is always going to be in this case. It's better so that the case is more readable. Handle function type will take the name, the unique name that uniquely identifies this function, and the fun type, the function type. And what will it do? It needs to return. I don't need to do that, I think. I just need the function type, which I already have. So this is just returning a tuple that contains on the first element the function type, and on the second element the name. Okay. Handle variable is going to be a bit more tricky because I have a name here. And I guess I have the function type, but that's... I can disregard the function type entirely, I think. Because in the case where... in the case where I have... in the case where I have the function as a function pointer somewhere on the stack, the register will contain the information. So I don't need to duplicate that information. That being said, it might be easier. It's guaranteed to be the same anyway. It might be easier to just... it depends. It might not be, because here I have a let variable. I know it's the correct type because the type checker has already happened. Yeah, getting the type from the register might allow me to not have to do this kind of nonsense again. So maybe I will change this to be either... here's the register that contains the thing. It has the type information that you require. No, I will need to still do a case thing because I will need to be able to decide whether the register is actually a function type. No, I have to do that kind of checks anyway. Let's keep it the way it is already written. Okay. So here I have another path. And here there is only one valid type for this, which is function pointer. If it's not function pointer, something went wrong. So it has to be a function pointer which contains the function type, which is what I want. In which case I do something. And in any other case, that's an incorrect type error. There we go. What do I do in this case? I have the function type. I need to know the register in which it is stored. And that's where things get complicated. This is where I have to do a lookup of like, okay, to that local name, what register is associated? And this is where we're going to have to do a bunch of lookups. So this is going to be how do I name this function? I have named retrieve something functions that look into the result of the type checker phase to get information about functions and structs and types and so on. This is not about retrieving something from this broader context. This is about performing the logic. It is not about just retrieving things. It is about modifying the state of the IR to figure out from which register to read a thing. How did they call that in the research paper? I think they call that read variable, which is, yeah, read variable, which is not very, which is nothing wrong with it, but I think I want something in name that also conveys the fact that we're modifying the underlying control flow graph. Like we're doing more than just doing a read, just doing a retrieve. Is that a fetch? Can I use fetch? Does fetch imply... Resolve. Resolve is a good name. Resolve. So this is going to be resolve name, I suppose, in this context. So resolve name of the identifier in this context. That will kick in all of the complicated mechanism that we don't have yet. And that will ultimately modify everything under the hood, but it will give me the register. And with it, I can return a tuple which contains the fun type and left of the register, which I am tempted to rewrite as a one-liner. This is constructing a tuple with fun type after applying left on f mapped into a resolve name of the name. Okay. So that is... Wait. Oh, I did not change. This is retrieve function info. There we go. So this presumes the existence of resolve name, which is one of the most difficult things we're going to have to do. But providing that resolve name exists, this supports function calls, and it also supports function calls from local variable that contain function pointers. So now I can go back to call expression, and that's the same. Okay, so now let's make this compile, because I can try function calls that don't do function pointers just yet. Resolve name doesn't exist. I will at some point break this file into multiple files, because for now we've been putting everything together and it's kind of a mess. But we are gonna need resolve name, which for now is gonna be unimplemented, and that is the next big thing that we have to do. Field name is not... Field not found error is not something that is relevant in this, so I'm just gonna remove this error altogether. A bunch of unused things. We take those. This, okay. I don't actually need the register type. I only need it as far as I need the make register. So I can probably... There's something about doing this like this that makes me think that traverse bind into traverse. Mm, there might be a way to do better then. Nah, maybe not. That's fine. Okay, so register type no longer required. So the function return is a maybe type. I traverse this maybe type with translate type, which gives me a monadic maybe of the value which was a maybe, so that's a monadic maybe of the maybe. I bind that into something that will apply a function on the monadic value and will return something in the monad as well. Takes the maybe thing, and indeed I traverse join like this. There we go. This binding for fun type shadows. Okay. FT it is. Define but not use, that's correct. Define but not use, that's easy to solve. Fun type also conflicts, so FT it is. That should be all. And those were warnings as errors, so that should be everything. Okay, so now we can try this thing I wanted to try earlier. No, I can't try that yet. Wait, no, I should be... No, I can't do that yet. Because field access expressions are done, but this would require doing a lookup into something, and I can't do that lookup yet. No, but I can do something better. Okay. I can make this be a call to foo1, and that should allow me to test function call to something that is not a local variable and therefore doesn't need to be resolved as a local name, which is the complicated part, and just gonna be linked at linking time, and test what the field extraction stuff looks like. We encountered an internal compiler error. Encountered an incorrect role while expecting a type. I found a type parameter. How did I find a type parameter there? With a name? What? What? What's happening here? Why does type parameter have a name? Oh, it's for your type. Well, no, that makes no sense. Why does type parameter have a name? Oh, it's pointing to... It is pointing to the function that declared it because I want to be able to... Yes, that's what it is. That's where it is. And as a result, the type parameter is pointing to, yes, the struct from which it is coming from. Okay. So there's a place where I encountered a type parameter, despite the fact that I'm looking at resolve stuff, probably in looking up struct information. So that would be at line 390. That is translating a type. Fascinating. So I am calling translate type. I don't have has backtrace on a lot of things, so I don't have enough backtrace information to know which translate type I was calling. But in all likelihood, I was calling it on something of a struct. So I have a field access expression, or maybe I have a function expression. Which which thing was? Where do I have a type parameter? Oh, it's a type parameter of the unique thing. This was working, so this is as part of this. It is, I am looking at a call expression, I am looking at the function type, I retrieve the function information, and the type it gives me is not instantiated properly and contains something that is wrong. So when I do a retrieve function info, and I am in the case of the top level declaration, I am here. I return this function info there. And here I do a let's get the function return type. No, this is going to be fine. It's the get field that's wrong. It's a get field that's wrong because when I do a retrieve field info, when I do a retrieve field info, I don't do the instantiation here. That's what it is. So here, when I arrive at this thing here with the field type, I need to do. Okay. So I need to do the same thing I've done for the translation. Because yes, when I was doing the translation for a struct, it's like, oh, I have a struct, I have the information, I can do the replacement on the fields. But here I have extracted the field and then translated it. I guess a solution would be to call. It's gonna be ugly. Let's do it this way, I guess, and I'll deduplicate the code afterwards. I need to do the parameter mapping. I need to do this basically. So when I do a retrieve field info, I have found the struct info. I need to do this. The parameter mapping is from list of the struct parameters of the struct info with the path parameters. And actually, I don't need to do that here. I don't need to do that here. I already have the struct info. Perfect. So when I am in this case, the field type needs to be substituted with get mapping of the struct info and get mapping of the struct info is going to be this thing here, which I'm gonna inline because it's gonna be fairly short, because it's gonna be struct params with path params. There we go. So now I will fix the thing, and this can go away, and that now should work. Okay. Which function was the interesting one? Foo2. So foo2 is invoke something that will give me a struct that contains a character. And this is invoking something that has a unique name, so it's going to be linked later on. This is not invoking a local variable that contains a function pointer. And it's invoking foo1 with no argument. And then it is the atomic expression get field that will put in register C1 the result of getting something from this register S0 at index 0, and then we return the value in the register C1. There we go. So that works. And we're also handling generic functions in the meantime because, you know, let's do everything at the same time. Now, next, I think I want to do the path expression because that one we can do, I think, fairly. If we do the same thing that we've done for a function expression, which is to assume that the resolve thing exists, which it doesn't, but you know, if we assume it does, then it should not be monstrous to do because a path expression is just that. It's just a path info. What do I do for reference, actually? Maybe for reference, I should just... I think for reference expressions, I should handle them now. So path expression is just a path info, okay, and a reference expression is just a path info, okay. So that's path info, that's path, that's just resolve path, I think. And a path expression should also be just resolve path, I think. Except it's not called that. What is it called again? Resolve name is what we said. But this is not a name. So actually, no, this needs to be resolve path. And resolve path will be extracting the name out of the thing and deciding how we want to resolve it. Okay. So resolve of a path is something that will take a path info resolved and give me a lowering M. It will give me... Does it have to always give me a register? Is there a case where it gives me none? Can I guarantee that all names must give a register? If I end up having a path expression, it could be a bunch of different things. Not all of them will be a register, I think. Because this could be called... No, all of them should give me a register, I think. Okay, so resolve path. And this is gonna be a thing we have seen a few times. This is gonna be this kind of stuff. What kind of path are we trying to resolve? A top-level declaration? That could make sense. That means we are trying to resolve a function. And we will want that to be a register that contains the value of a function, which we don't have an instruction for, but we can do. But that's the only thing that would make sense. Maybe a constant? But I think at this point, constants are all inlined, so no. So this would be... Yep, handle declaration. Works for me. A let variable. This is where we simply have to do... Wait. Yes, it's coming from a let variable. So I know that the name x that I'm looking at here was introduced as a variable. This is resolve name, which is our horribly complicated thing. Built-in function will need to happen. Function argument is also resolve name. Built-in function will exist at some point. Function pointer is a type that doesn't make sense. Built-in type doesn't make sense. Type parameter doesn't make sense. Placeholder doesn't make sense. Okay. I'm gonna copy some of that just because... Wait, which one did I copy? Probably this one. I'm gonna copy that. Something that annoys me a tiny bit, one of the reasons I've struggled the most with the analysis was how do I represent the output of the analysis in a way that makes sense? And here we are facing some of the issues there where the representation of my AST of the output is not it's not great. And I end up having to do a bunch of like, hey, in this context, I know what kind of thing this can be, but I still have to do a case switch on the thing and have a internal compiler error, an error, a partial thing, and half the paths. That's kind of annoying. And that suggests that our representation of the output of the analysis phase is bad. And perhaps it means I should rewrite it at some point. Perhaps, for instance, I should distinguish between value things and type things for the roles, where when I'm looking for a value, I know I have a thing that can be a value, or I'm looking at a thing that can only be a type. Like, I don't have this problem of having both of them in the same namespace and having things that can be either at all times. There's a lot of things I think I can do in terms of representation of this that can be better. But this is what I have at the moment. It works as is. I will probably revisit that at some point, but with the benefit of hindsight, I think. Not right now. So we need to handle the declaration. That's the big one. Everything else is just resolve a name, which is going to be the monstrous difficult thing. Incorrect type error when resolving path. We find a declaration. The only thing it can be is a function. Nothing else makes sense. Nothing else makes sense than a function, so it has to be this case. Missing function declaration error, yeah. Perfect. Yeah, all of this is correct. What do we do in the case where we find a function info? I'm gonna need a new instruction in my IR. I'm gonna need assign an address which gets a name and a register, and we'll put the name and we'll put the address of that thing in the register. So here we find the function. We have the function type, which can be translated. So we do that. And we do that for the register. So the target will be make register of force type of wait, can I just do force type will do a translate type, and it will attempt to translate a declaration, and if it is, it will try to translate a function. Yeah, I think the type checker will have resolved for me. The type checker will have resolved for me what the valid thing here is. So I think I don't need to bother here. When I resolve the path, if it is a top level declaration, then if it is a top level declaration, I know it's a type. I know it's a type, so I can do something a lot simpler here. I can do force type of the path. Like, okay, I have the path to whatever the thing is. Give me the corresponding register type that corresponds to that. And if it's a function, that the type checker will have solved that for me already. And I have the name, and this is going to be purely a append instruction where we are going to put an assign where this target register will be assigned the unique address after the linker does the thing that maps to that name. And that should be all for resolve path, which means we could almost try already function pointers, except I don't have resolve name, and that is the thing on which everything depends. So, at 1 a.m., after 5 hours of streaming, let's do resolve name. Let's do the big thing that is missing. Since we don't have assignments yet, we only have the simple case to handle. So we could try the simple case just to check that everything else works. So this is going to be given an identifier. Give me the register that it corresponds to. Okay, so there is the easy case, which is that variable is within the current block. That's the case that's trivial. So we can start with that case. I will need the name of the current block. And I can do this is going to be a uses where I get something from the state. I look at the registers, and what I do on it is a lookup, a map lookup, where the key is the current block and the name. Is there something in this block that defines what this register is associated to? Was the let that introduced it as part of this block? Was it given as an argument to this block? If the answer is yes, the end. I have found the register. On nothing, the value was not found in this block. Then we need to search it recursively. And this is where things get complicated. So this will be our go, I suppose. And I'm almost tempted to stack another state on top of it just because I'm going to do looping in the graph, which means I will want to keep track of which things I've already visited. Actually, what happens? Okay. So I know I don't need a state. Okay. But I will need to know which label we're searching because I'm not going to modify the current block to search. That would make no sense. Okay. So we go and we search the name in that label. So if we implement things the way they are here, if we implement things the way they are here, I need to first test whether this block is sealed. So basically, go is if M is sealed of that label, that means that's the best case. I'm gonna actually do it here in line because if we are sealed, that means we know all of the parents. And if we know all of the parents, that means they know all of their parents. They're all sealed by definition, I think. I think it's impossible for a non-sealed block to be the parent of a sealed block. No, that's not true. That's not true. That's not true. I need to be careful. So here if it is sealed, then that means I have all of the information. I can do. I can go do the thing, basically. I'm actually going to do it as an unless. If it is sealed, then introduce temp register in that label. Otherwise, do, and here is where the main thing will go. Introduce temp register. It's a thing I've called potential. That's not great. Is that supposed to be hash out of role? Is that correct? This might not be. This might not be correct. Okay. But the point is this. I need to be able to... Oh, sorry, I hadn't seen your question. High CPU cache hits. I am not sure. Probably. Really depends on what the compiler does under the hood. Like it is a compiled language with like several decades of performance put into the compiler. I would assume that yes, it does. It really depends on like the memory layout and things, but like I don't think I can give a generic yes no answer there. Okay, wait. So train of thought back. I was looking at this. So this is gonna be. I'm gonna make a fake. I'm gonna make up a fake register for later. That I'm gonna then fix at a later stage when I have all of the information. Okay. And when I seal a thing, which is this, yeah, that's putting a value. Okay. So here I would need to know, can I know the type of the thing I'm looking for? I can know the type of the thing I'm looking for from, because when I call resolve name, in all the cases where I call resolve name, here as a function pointer, here as a let variable, here as a function argument, I always have the type. So I could, in theory, always compute the register type so that if I have... Yeah, I think I need to do that. So this, the potential, will be that. Basically, it's going to be the same thing, but it's not going to be definitive because it will depend on the block being sealed. So that means that resolve name, every single resolve name needs to be given an IR type. So this one will be computed from the function argument type here. And the name, okay, so that's var t, this is arg t. I could do a flip resolve name over a force type. Well, not exactly a, yeah. It's not very elegant. Having to do a flip feels wrong. I could, yeah, the type is second argument, actually. That makes it not a flip. That's fine. Yeah, a bit inelegant, but that's fine. That works. So we have the name and we have the register type. Okay. Resolve name, resolve name. Here, likewise, I have a function pointer that contains a function info. And that means I will need to resolve name, and I will need to translate that into a register type. And translate type knows how to translate a function pointer. So that's gonna be, I'm gonna do the path here. Let's do it in several steps. It's gonna be a bit more readable. Register type is gonna be the force type out of the path that we got. Register target will be, no, register will be the result of resolve name with the name and the register type. And the result will be a tuple that contains the function type and left of the register. Oops. Okay. That's all the call to resolve name, so that's done. So now I have the type. So if I have to create a register ahead of time, I know the type of the register I have to create. That's fine. So here, introducing a temporary register in a given block is, okay, this block will need to figure out where the name foo comes from later. So for now, we make a register with the register type. And we introduce it in the potential registers. We modify the state by doing an insert of, we're doing an insert of in this block. Label, it's fine. In this block, this name is associated with that temporary register that will need to be sealed later on, and we return the temp register. Okay? Otherwise, if we are not in a block that is sealed, actually, oh yeah, no, this is the case where we know the current block doesn't have it, and therefore we need to go higher. So here, this is gonna be, let's get the parents from the current block. So I guess block here is gonna be current block info. Nope. It's going to be block info for that label because I am not necessarily on the current one. So now I have access to the parents. And now I can look at the parents. If there is only one, then I don't have to do anything fancy. The name must come from somewhere. It is not from the current block. It must be coming from the parent block. So go parent. If there is literally anything else, it cannot be empty, but you know, we're not going to deal with that now. What that means is that I can traverse the list of the parents with go, and that's going to give me a register per parent. But I need to do something else first. I need to put in this. I need to put a block argument in this thing so that I can stop infinite recursion to avoid cycles. So, what that means is, in this case here, I will have to register this as a block variable. So, we create a register. So it's going to be block argument, which is going to be make register of the register type. I'm saying it can come from more than one place. I'm going to take it as an argument. It can come from more than one place, therefore it needs to be, okay. What happens if not all parents have a definition? That means one of them will have to not include the value for the thing? It's kind of weird. That means I have to push empty registers on the stack. It's gonna be weird. Anyway, I register an argument. So I'm going to do the same thing that I've done for function. At the top of the file somewhere. Here. Here, we append the argument. So this block... that's annoying. That is annoying. I only have append argument for a current. I don't have a lot of. I haven't introduced functions to manipulate a block which is not the current one. Okay. So maybe append argument actually should take the label. Let's do that. So append instruction will always be in the current one, but append argument maybe actually takes the label as an argument. And just does that. Okay. Append argument is only in use. It's used in a few places. So append argument here is on the start block, on start label. Here it's on the current one, which is the resume label. I guess I could make an append argument to current to avoid having to do this. Later. Okay, so I've added a argument to the current block. I've registered it so that future lookups here succeed. So if we end up doing an infinite recursion, oh, this needs to be part of the recursion actually. So this, yeah, this needs to be that basically. And go becomes this thing. Yep. So I do that, and on nothing, I do that, and unless it is sealed, in which case I do that, I do this. So okay, either I found the register in the current block. Perfect. I can return the value. I can say, okay, oh, in this block, this name means this register. Here's the register. If that gives me nothing, then am I in a sealed block? If the answer is no, I cannot continue looking for the thing because I don't have all of the parents of the current block yet. Therefore, I introduce a temp register that will be resolved later. Otherwise, I am in a sealed block. I know all of the parents of the current block. I can go recursively. So, if there is only one parent, I can simplify immediately, as in, there's no need to introduce a block argument or anything like this. Just go immediately and give me the result because the value will have to come from the only parent. Otherwise, I create a block argument. I add it to this particular current block. I register it so that now, if there's any cycles or recursion, I know where the value is coming from in the first place, which is there. And now I think, traverse. Yeah, basically. Now I need to figure out. Now for each parent block, I need to do a lookup of like, for them, what register is this? And add it as an argument. Okay. Do I have the guarantee that all of them will have it? I don't. I don't have the guarantee that all of them will have it. I need to handle the fact that sometimes a block will not contain the value. Actually, is it possible? Is it possible for only one parent to have a value? That doesn't make sense. Yeah, I don't think it's possible. I don't think it's possible because if it were, that means there's a path in the function that arrives at a thing where the value has never been declared. That is not possible. Okay, there will always be a register for the value. So that's fine. So for each of the parents, what do? I recursively go for that parent, which gives me a register, which I'm going to call the source. So I know that from that parent's perspective, the source was this thing, which might be a temporary one for now, for all we care. And for all of them, I must now add that as an argument because I've added an argument to this current block. So that means I need to change the terminator for that parent if it is I need to change which the terminator that points to that thing, I need to change it to include the argument. That's not trivial. Okay, I can do that. I will need to have block info in scope. So the block info for that parent, its block terminator will need to be modified with, for this append terminator argument, for this label, and that's the argument to add. Append terminator argument for a given label and a source is a function that takes a terminator and fixes it. If it's a jump to a target, then that's trivial. It is the target where the target arguments. Did I make lenses for target? I did. The target args is modified by adding this new source. If it is a branch, well, I guess it is a jump with this. If it is a branch between a target 1, a target 2, and a branch register, if the label is the target label of target 1, then the result is a branch in which target 1 is modified so that the argument is added. Can there ever be a branch in which both of them? Nah, that can't happen. It can, but it can only happen later, I think. No, it can't. It cannot. I was wondering if, like, an if with an empty block, if, and there's nothing in the block, that's a branch to either that block or to the end, I will still not simplify because, yeah, I will not simplify the blocks. Okay, that can't happen. And the target 2 is unmodified. And in the other case, which I'm not plan to debug, there's no point in trying to. So I'm just going to say that. In the other case, it must be the other one. So the arguments have been modified. Okay. Any other terminator will be left unchanged because it's either a return or a panic, which is impossible, but I don't feel like handling it. But I should handle it. So report an internal compiler error. IR lowering. Parent of a block does not point back to it. Where parent terminator is this, and child label is show of the label. Okay. I think that's all for resolve name. It is missing a few things, including the simplification of block arguments. There's going to be places where the block argument is not necessary, and therefore we could remove it. That being said, the register allocation functions as part of the code generation will do the same kind of simplification. It's not that bad to have extra arguments. It's not the end of the world. Okay. Yeah, and try to remove. What this is basically saying is before doing this, before doing this thing of like actually modifying the terminator of the parent, I could maybe realize that if all of them are returning the same thing, so if the value, if the register that should be targeted is like the same in all cases, there is no point in creating a block argument. So maybe I should do that. So that would be registers sources sources will be the result of traverse go parent. Now, what I want to check is if they're all the same. So unless length of group of sources is 1, which will be the case if all of them are equal, because group of values that can be compared like 2 to 2 to will be 1. So the length of that group will be 1. So if they're all the same value, I don't have to do anything. Well, I have to do something. Because this has to always return a register. So this has to return a register. If they're all of the same, if they're all the same value, then I just want to pick the first one. Head will crash, but I can just do a list to maybe of sources, and on nothing, um, name not found error. Otherwise is where we need to do all of that nonsense. This function is getting very nested. Incorrect terminator error. Okay. And the error I just introduced as well is name not found error, which is an internal compiler error because we've already type checked the whole thing. Okay. So here, in the case where they're all the same value, there is no need to create a thing. I just get the first one, that's fine, yeah. Otherwise, I have to go to the thing. And now this is for, I'm going to need to do a thing. I'm going to need to zip parents sources. And I will get a parent and a source. And for each of those, I will go do update the thing. And at the end of all of that, I can return in this case here, I would need to remove the argument that I've added here because it's no longer needed. Okay, so I'm not going to do this optimization for now. I'm just going to do that. I'm not going to do the optimization. Okay. Because I don't want to have to deal with removing the block for now. Let's do just like this. And at the end of this, I return the register, the block argument. Okay. That should be everything for resolve name, except for the seal function for blocks. So we're not out of the woods yet. We're not out of the woods yet. Oh, that's pleasantly surprising. Aha. Yes, I have added an assign, which is the assign address, and that's That's going to be just that. Pass error on equal. Yes, this is supposed to be an arrow here, and so is it here. Block info is part of the monad here that I did not block info. Arg name doesn't exist. This is because this is not arg name, this is name. Register, it's actually called a block argument. Parent doesn't exist, and I don't need to do that anymore anyway. Okay, so let's do this differently. Now, I'm gonna do delayed arguments. Things I've potential is terrible. Placeholder, that's the word I wanted to use. There we go. Potential. That's placeholders. Oh, however, I will need to make this differently. This will need to be a double hash map. Because here I will need to be able to ask what are the things for this very specific block. Does it even need to be a hash map of identifier register? Actually, does the paper address this? No, but I need to handle this. I need to handle this. Okay, first, let's finish fixing potential doesn't exist anymore. This is placeholders. Potential doesn't exist. Perfect. I need to handle something else. I need to go back here. Here is the case where I'm saying, oh, this block isn't sealed. I don't know all the parents yet. I cannot guarantee that I'll be able to find the register from which that name is coming from. Create a placeholder. That is slightly incorrect. I should only create the placeholder when it doesn't already exist. So this becomes a uses ls placeholders, and I do a lookup of the label followed by a lookup of the name. And if this gives me nothing, it means either there's no map for the placeholders, or there is no map, or there's no register for that name. So in that case, I need to create a register. The placeholders have to be modified. It would be a lot more convenient to have only one layer of map, but that makes sealing a block a lot more complicated because then I have to iterate over the entire map, which defeats the point of it being a map in the first place, I guess. So I have to modify. So insert with. I am gonna insert with, and that means I'm gonna insert a new hash map. The value of which will be a singleton map that to this name maps the temp register. And the question is, how do I combine the old map and the new map if I ever have a collision? Because there was already some temporary registers for that block. It is going to be a union with concatenation. The keys will be merged together and the values for the keys will be combined like this. Wait. Those are not monoids. Union is what I want, because I have already checked that there's no such key. So yeah, union is what I want. Okay. Okay. That's done. Which means here I can do uses placeholders, and I do a lookup of the label, which gives me a monadic maybe thing, maybe hash map, which means I can do. I'm gonna read in several steps. So that's gonna be the placeholder args. That's that. And now I'm gonna do a for of a maybe to list of the placeholder arguments. Well, that's not great. No. Is a hash map a monoid? No, I don't think so. It is a monoid. So I can fold a maybe hash map into a hash map. And now, actually, it's going to be a traverse with key. Flip M traverse with key. And for each name register, we're going to do some shit. I think that's basically exactly the same thing that we've done for the general case, which is like, oh, we have this register. make it a block argument, go through the parents and fix their. So I'm gonna make that a separate function, I think. Let me see what the paper says for the seal thing. It's just the add fee thing. So that's exactly what we want to do. So it is literally just doing the source thing that we've done. So it's this. It's the append argument registers. It's just that. Okay, so this whole thing I will make into a separate function. So here, this is going to be register block argument with a bunch of stuff, including the block argument. And this function is going to return the block argument at the end. So here, this is going to be something like that. It's going to have the label, the block argument. So I need the label there as well. Okay. I append the argument to the block. I modify the registers of the whole function to insert that particular register. And I need the parents. Okay, so I need the label. I need the register. And I need the block, I suppose. I can probably do that, and this performs an action in the lowering monad. Because I don't need to return shit here. And this will be the block here. Okay. Actually, I could probably just get the parents. So that's just a list of label. But Go... I don't have Go anymore. Okay. Takes an extra argument, which is the label, result name in the label. And that is this function. And resolve name is just resolve name in the current block. Now it's this function, and I just need to reintroduce a where block for introduce temporary register. Now, I don't like this. It's ugly. Okay. Append terminator is no longer something that's required as part of this function because it becomes a thing as part of this one. And this error becomes this. Okay. So now we have the thing that puts the stuff in the other stuff. Register the block argument, which updates the parents to make sure that they point correctly. Which means here I need to do this and I need to give the parents, which in this context will be the block parents. And that's everything. And with that done, I can go back to the seal function, seal block here. Now for each placeholder I have found, I need to just I need to void. Is there a traverse with key underscore? There isn't, so I need to void that to avoid a warning. And for each of those things, I will be doing. I need to get the block info because I need the parent. Wait, am I only doing that to get the parent once? No, because I do this optimization. That being said, I could still not bother with this and re-get the block parent here. That's perfectly fine. And that means here we're back to having block parents. And that means I can remove the parents from this argument, from this, and from this. Okay, which means this becomes even a simpler call, and that becomes a lot simpler here on top in seal block, because this is just that's the identifier and that's the identifier and the register. This needs to it needs the identifier as it. Yes, it needs the name. Which is here, it's the name. And that means I can rewrite the horrible thing at the top. This is a void of traverse with key, and the function I'm applying is just an uncurry of register block argument for this label. Of the placeholder arguments. Which means I could also even consider doing that this is void of use this that thing. Now, because here I want to do a fold of the placeholder arguments. There we go. And that should be everything. Go no longer exist. This is now called resolve name in, and I need to give the parent the name and the register type. Go no longer exist. Well, if I have the register, I can trivially get the register type. So this is gonna be resolve name in parent, and the name is, the label is this. The name is this, and the register type will be register type of the register. And if that's the only error, then I'm not going to do that anymore. I'm just going to inline it. This made more sense when there was more than one error in the function, or when it was in an inconvenient place. Actually, name not found is no longer used. Great. Oh, because register block argument requires label identifier register. And here I am uncurrying it register, so it should be... Huh, okay. So something is wrong. So traverse with key. Traverse with key expects a function that given the key... Oh yeah, I don't need the uncurry. Nice. Couldn't match register with maybe register. Resolve path gives me a maybe register. Why does it do that? What is the case for... Why do I have a maybe? No, it's the other way around. It's the other way around. Okay, that's good. It's a good problem to have. This always gives me a register. I just need to adjust it. Because it would be wrong for it not to give me one. Same thing here. And since those two are exactly the same, I'm going to put them together. Or I might move the reference one, actually. There we go. Because the reference thing is purely a type checking kind of thing, the information will be available at code generation. So it will not be... Will it actually be... maybe the information won't be there at code generation. Maybe I'll need to capture that. Okay, so maybe this is wrong, actually. I'm just gonna put it back as unimplemented. Although it will be based on the same thing, so... This gives me a register. Ah, but this must give me a register. I guess here, since I know the thing, I can just avoid that and pure target. This is a type, this is a function argument, so I need to do a function type argument, function argtype, I think it is. Okay. Resolve name in, I will need to give it, so I need to do okay. Label is get the current block, and then resolve name in label name register type. Ah, this is okay. Unless m is not the same thing as a, so I need to do an if m here. So if it is sealed, then search recursively in the label. Otherwise, I might actually not need to give. Yeah, label is now an argument to the thing, so this is just search recursively. Otherwise, introduce temp register. Search recursively is okay. And introduce temp register no longer needs the label, and it's this nonsense. And I'm gonna introduce a thing. I'm gonna break down this line. I don't like it. So placeholder will be the result of doing this. Which is still gonna be big. It's still gonna be big. But now I can at least remove that. And I can do placeholder and on nothing. It's worse. It's worse. Let's keep it at one line. Okay. Block info is applied to too few arguments. Am I using the wrong function? Oh, block info is the lens. Get block info is what I want. And it's not in scope, so I need to remove the block info and put get block info. Other places where I do a block info, this becomes a get block info. Is there a thing for like parents? Because that would be a lot easier. Yeah. Parents label. Yeah, that's what I want. It's gonna be. Okay. So what I want here is I just want the parents of the label. And K's parents of, and otherwise, yep, there we go. And the void's having to do a bunch of, okay. Scope. Okay, so block info needs to be there. So I can go back to here. And I can go back to putting block info in the output, but not get block info. I'm missing one argument here, which is the register. And I'm missing it here as well. Okay. Defined but not used. We are now at the warnings. Correct definition error. Defined but not used. Okay. We are at the point where things could actually start working, which would be nice. Append terminator argument. The label is not required. Because the label I already know. That's okay. This compiles. We could be at the point where we actually are done with the main generation of the AR, which is where I wanted to finish this. Now we need to debug, of course, but we might be done. So let's try some very basic cases. Can I remove all of that nonsense? Let's try a function that takes an argument which is an int and returns that argument. That's a name lookup. Oh, we're not done anyway. We are not done because of the assign. Okay. So indeed, that worked. We did find that the register that for that return was the one situated here. Now, let's do something more complicated. Let's introduce a if false, do nothing, else do nothing, which is going to create a bunch of new blocks, which means this X will have to go through a bunch of things and create a block argument. So label 0 has an argument, which is the argument to the function. It assigns false to a new register, branches based on that register. If true, we go to 2. If false, we go to 3. Both of those contain nothing and just jump to label 1, which is the post if, giving it as an argument I0. This is the register you should be using for the value you're looking for. And indeed, this block takes as an argument where the value x is coming from and uses it for the return. We don't do the simplification yet. If we were to do that, we would identify that, like, oh, actually, all of those, it's I0 in both cases, therefore it's not required, and we could simplify. But the register allocator probably will do that for us. It might be worth doing the simplification, but it might not be required. But that works, is the point. So now, I don't have a sign. So I can't do some of the stuff here yet. But can I do a function b that takes an int, returns an int, and returns x, and a function c. This one does x plus 1, let's say, because I want to try mathematical operations as well. And here, let's say this is x equal 0 as int. So it's a cast of... so now x greater than 0 and x less than 5 cast as int. So 0 or 1. Okay? So complicated functions. And both of them are functions that take an int, return an int. Let's say that let f equals b, a function pointer, if false, because, well, if x equals 0, f equals c. Return f of x. We are trying function pointers. Let's go. Okay, we did get something wrong. But that's just not implemented yet. That's not the end of the world. That is at line 316. What is that? A sign. Yeah, of course it's an assign. I don't have a sign yet. So some of the stuff I can't do. So instead, I am just gonna do this. Internal compiler error. Okay. Encountered, so this is at line 382. Incorrect type error. So here we encountered something. So the path, the path name was one of those. Built-in type, type parameter, placeholder, function argument, something. No, it wasn't late variable. What are you talking about? Oh yeah, late variable can be that. Wait, how did that happen? We did a translate type. We did a translate type on something that happened to be a let variable. So I had a value and I treated it as a type. That's the mistake. That's the mistake. This must have been... This must have been in the resolve name, I suppose? Or resolve path, actually, probably. Yeah, because this might not be the role here might not be it might be the yeah, I think that's the problem. Okay, let me check with a quick git grep. Yeah, I think 90% of my errors are having the same types for like value space and type space, which is a bit annoying. So a let variable. No, it would be the role would be it is created as being the expression type. So no, this is not where the error is. Okay, so let's do a thing. I'm gonna add translate type. I'm gonna say has backtrace, whatever the proper syntax for that is. Which I don't remember. Is it internal ice? It is GHC has cold stack. There we go. And I'm gonna put that as well on the force type. So that I know which one actually crashed here, rather than trying to figure it out by reading the code. It's getting unwieldy. So force type called at line 430. Okay, so it's this one. Aha, so the function pointer. Aha, yes, of course. Here, the force type, I am passing the path, which is this path, which is wrong. That's the variable path here that I need to be giving, which is going to be the var type. Okay. Aha! It compiles. Well, it compiles. It gets that far. So let's first have a look at B and C. B is a function that gets an argument, which is a register here, which is an int, assigns one to a new register, adds those two registers together into a new register, and returns the value. C is a lot more complicated. It starts with a label 0, which is the argument. It's assigned 0 to a new one. It compares greater, and then it branches because the Boolean end short circuits. So if it is already true, then it has to jump to label 1 to do the other one. Otherwise, it's false. It doesn't need to and jumps to here, giving it the value I2 as the, which is going to be false as an argument. Oh, that's wrong. It's almost correct. And here, the second thing is, yeah. Okay, so I have one trivial mistake. I like the fact it's just like function pointers work that despite the fact that I don't have the type for them. There is a tiny mistake I've just identified in the Boolean comparison stuff. Where are you? Around here? Compound assign? No. No. Basic binary operation? Yes. Basic binary operation, I think, always create the register type. Yep, there we go. I assume that the type of... I assume that the register types must match, and I assume that... Which is not necessarily... Yeah, I don't need to do that at all. The only thing is, I need to know what the type of the result is. So it needs to be given as an argument. Because here I was assuming, oh, they need to both match, and if they're both int, then the result is an int, which is incorrect. Not a big deal between int and boolean, but still, that would be wrong. So now that means every single call to basic binary operation, there we go. That's an IR int type. And those are Boolean type. So the result of a comparison is a Boolean. Okay, should be all. File. There's one that's wrong. Compound assign. What are you on about? Because compound assign will also need to know I think all of the compound assigns are int operation, so I think for now I'm just gonna let's be correct. Let's do that as well. Let's not be lazy. The compound assign will all be IR int type for now. I mean, all of those will always be, but you know. Okay. And now we are branching on a Boolean B2 because we fixed this. And now we properly have the Boolean end typed properly with the registers here. So that works. We have name lookup working, and we have function pointers working. We have almost everything working. The last thing we're missing is assigns. There's something I haven't tested yet. I haven't tested the complicated case. I haven't tested the complicated case. I need to test it. The complicated case will be... but I don't have an assign yet. Without an assign, it's going to be very complicated. But I can still try it. If I do this, and then I do a while true that does nothing, this block in which... No, I need to do a while true break. This block will have more... this one will have more than two parents, so I will need to know both of them. And the while condition will be sealed after being processed to avoid infinite recursion. So this is where all hell could break loose. It could do an infinite recursion. It could fail to register the placeholders. Like things could go very wrong here. So label 0, we assign the address to this f1. Okay, and that's the address of the function b. We assign true to b2 because that's the condition there. And then we branch. Oh, my block simplification thing has done some work, I think. Uh, and if b2 is true, we jump to label 2, which is the loop body. Otherwise, we jump to label 3 with an argument which is the f1 with f1 and I0. Huh. Why do we need 2 of those? That's the argument. Oh yeah, that's the x. We need the x as well. And here we also give f1 I0. And they're both given as like f3 I4. That works. It works. Oh. If I do the assign now, it's unreasonable, but it means next week we can just immediately move on to code generation. We could be generating images by this time next week. We could have the pipeline by this time next week, basically. It's almost 3 a.m. I probably shouldn't. So assign. Assign is the one I am the least comfortable with, because that's the one where I'm going to need to figure out there's going to be an easy case and there's going to be a very complicated case. And the complicated case is going to be several fields in a row. Like I'm doing x.a.b basically. How do I translate that into a series of values? That's going to be very complicated. And it's also going to be a bunch of horrible. Since really, I should really rethink. I have this thing where like I have my AST and my past and my AST resolved, and it has a lot of upsides to be using the same kind of stuff on both sides. But maybe if I were to rewrite all of my resolved stuff to contain a lot more information rather than containing a bunch of paths, restricting them to the values they can be, I would remove so many places in the code where I'm doing a case that just checks for something that I already an invariant I already know. I think yeah, some of the things I will at some point in the future want to redo is I want to replace happy by megaparsec because the syntax of Rust is ambiguous and I cannot have the proper Rust syntax at the moment because of it, which is very annoying. And I will want, I think, to change the interface I'm outputting. I will want to change the kind of how the AST, like how the output of the analysis is represented, because the current state is not convenient at all. And I keep making mistakes between types and values and stuff. So I will have to fix this, I think. Now, basic assign, where are you? Unimplemented, there we go. So that one is going to be very complicated because the left-hand side, I think, if I remember correctly, my AST, and assign on the left can be anything. Well, it can be anything that can be a valid, um, It's not called left value. How is it called again? Um, an L value, yeah. So kind of an kind of a left value. It needs to be a valid L value, and there are few of those because there are few things to which I can assign something. But that still means I need to do a case of the LHS of no, actually. Fuck, no, actually. Yes, I have to do that. Okay, okay. I will have to do some kind of recursion for finding the correct register for something. Okay, let's do step by step. The left-hand side of a assign could be a path expression. If that's the case, then that's fairly straightforward. I need to figure out what register that is. So I need to resolve the name. I need to resolve the path, actually. So that's going to give me the register. So this is where I'm putting things. Resolve path of the path. And I will be appending an instruction, which is a assign. How did I call that in dir? I did not have something for that in dir. I guess I don't need to translate that into an instruction. It is enough. I get the register. I get the register, and what I can say is, oh, now ha, this is a problem. I need to Yep, I need to actually resolve. I need the name because what happens basically is an assign is not an operation really. It is a It is a. I am now saying that I whatever the register is, this is what that name should be known as in the future. So that means I need to do yet one more. Really, I think and I think that's why the analysis has been so slow. My representation of the output of the analysis is dog shit and will need to be fixed. So this is what I need to do. Where are you? Assign. There we go. So I need to get the name. And there is only two things that are valid as an assign to a path in a function. The type checker and the name checker have already gone, so there's no risk of it being wrong. The only thing that makes sense would be let variable or overriding a function argument. In both cases, the only thing I care about is the name. Do I have any report ice in this? I don't. Okay. Any other thing? Um, I'm gonna make it inline for now. This is an internal compiler error. Yet another one. For IR lowering, and the error message is going to be assignment to a path that is not a local value. And I'm going to add some debug information. I'm going to add the path, which is this. This again reflects all of those internal compiler errors, reflect the fact that my modeling of the output of the analysis phase is not great, but you know. Because if I had instead a smaller type that says, well, this is what thing we're assigning, I wouldn't have to do this case again. I think I'll just rewrite the entire output of the analysis when things start working. Okay, but now I have the name. That's the bigger thing. I can I will need to know the register, so I will need to know the source, not the target this time. I will need to know the source, which is going to be a force expression of the value. As in, okay, this value that we're assigning the thing to, what is it? What's the register? Where is it coming from? And with that in mind, I can now add to the registers of this function, of this block. So append register? No. Do I have, how is it named? I don't have a thing for that. It is going to be an ls registers thing. That's basically that. It's an assign. Where are you? Assign. There you are. Okay. I have translated the value of the assignment to into a series of instructions so that I now have the register that contains the value that should be assigned. And I can now say that in this block, so I'm going to need to know the current block. In the current block, this name here now maps to this source. And that should be enough for an assign to a variable. However, this is not the only kind of expression we will encounter, because we could also be assigning something that is, I think the only other thing we can be assigning to at the moment would be a field of a struct. I think that's the only other thing that we have. I can check by looking at all the places where we do an L value. That's not super useful. So that would be, okay, let's have a look at the few places in context where we use L value. A function argument, a function argument, a function variable. Okay. Wait, I thought field access expressions would be valid as L values. If I go back to core, and I look at a field access expression. There we go. Oh, that's the case of a constant. I want to look at this one. The L value-ness of a field access expression depends on the L value-ness of its own left-hand side. That makes sense. If I do a function called .x, that's not something I can assign. But if it is variable foo.x, I can assign. So that means, okay, so I can encounter a field access expression. And that's the last thing I have to handle, I think, and we will have done assign. So field access expression. What does it take again? It is the expression and the field. This is where it gets complicated. If I do a.b.c equals 4, I don't want the register that contains a.b to be modified. I want the register that contains a to be modified. That is where it gets tricky. So that means a field access expression. I should compute the value. I should compute the value. And then I should probably do some kind of recursion where I get the register of the thing that contains but isn't that the basic thing of the assign? Okay, I think I have it. I will need to know where the value is and recursively put it in the left-hand side until I have something which is not a field access expression. That is, I think, what I have to do. I'm going to move basic assign, which is absolutely not basic, out of this. Assign register. Okay. And then assign register will take a few things. It's going to take the left-hand side and the value. So that's going to be an expression a typed expression here, a typed expression, which is the other one, which is the value, and we'll return a lowering m of a maybe register. No, actually, this one will return nothing. This one will always be pure nothing. There is no register after an assign. Okay. So what do I do here? At the core of this, I will need to know the leftmost thing, and I will need to do a update. So I will need to okay. So this is always going to be compute the register, the source, which is I force the expression of the value. Where does this value come from? And then I go recursively on the left-hand side with the source, where go is going to be a function that looks at the thing and says, what is it? What do we do with it? If it is a path, then that's the most basic case. I have a value and I need to set it. Oh, but that doesn't work. If I have a field, if I let's think about the base case of the recursion. I have a.b.c. When I arrive at a.b, what do I want to say? I want a.b to be a set. So I need to know the register from A. So I need to know the register on the left-hand side to be able to say this is a set field. But if I'm on a.b.c, I don't want to do a set field. Oh, unless... No, I don't want to do that. Ah, God, set field. The recursive set field is a nightmare. Let's write it down just so I can see what happens. So if I have something which is a.b.c equals x, what is the sequence of operations I'm expecting? I'm expecting, oh, I need to get b out. So I need to get some register 0 is gonna be get a dot b. Well, okay. Let's assume a is actually register 0 or something. So register 0 is gonna be locate a. Well, we locate a and we say it's 0. So it's gonna be get b from 0. It's gonna be in 1. And at the end of that, what we're gonna be doing is we're going to be doing a set 0 b to the modified value of this. And the modified value of b will be, well, we need to get the C out of this. No, we don't need to get the C out. This is going to be a set. I modify the one, which is B, by setting C to X, which we're going to say is X. And then I'm going to say A here. So this is what's supposed to be. So I need to go left to right and then right to left, I think. Because if this were A, B, C, D, X, then one is get the field B from A, two is get the field C from B, three is set the field D to X. I don't need that, it's just that. And then it is set in register 1, I modify. Well, no, I guess it has to be a new register by virtue of being a single static assignment. So this set gives me 3. So now I override B in... No, I read C in 1 by setting it to 3, which gives me 4. And then I can obtain the result, which is 5, which is set in A, the field B, which is now 4. Okay, that's a nightmare. That's a complete nightmare. So basically what I need to do is I need to go recursively from left to right to get the leftmost thing I can modify it, and then from right to left, I need to set the thing. Okay. Okay. So I think it also depends at the top level. Do I want to handle things differently? No, I think it's fine to keep it the same way. Okay, so I'm missing the last part of this, which is get 0 and 0. That's just locating A, basically. Yeah, okay. I think I have to do something different based on the top level operation. An assigned to a variable is not the same thing as an assigned to a field thing, and I can't treat them as being similar. Okay. So let's look at the left-hand side. If it is just a path expression at the top level, that's just A equals B, that's easy. That's I find the name and I update the value of the register that I have found. to be this new value that I have located. Okay? Okay, so that's easy. Field access expression is where things get monstrous. So I have to do a bunch of gets basically to get the value on the left to the top of the thing so I can modify it and then do a bunch of things to the right. Yeah, that's what it is. And that will be the same for the index expression if I have them. So that means I need to. It's not that monstrous actually. Well, no, I need to know. I need to keep track of the registers so I can update them on the way back. So that makes it complicated. Ah, okay. This one I'm gonna sleep on because this one I don't know how to do, and it's 3 a.m. and I'm tired. I'm just gonna do the assign to a variable because I want to have at least that because that's enough to start doing code generation next week, and I'll think about the. Oh, yeah, that makes sense. Okay. This has to be. This has to be a non-maybe thing. So this has to always return me something. So I can just do an on nothing m here and report an internal compiler error, which is going to be IR lowering. Assignment did not yield a right assignment right hand side did not yield a valid register. And then I'll have something. Okay. Takes another type, the thing that I'm gonna ignore. This takes name and something that I'm gonna ignore. Yeah, I'm getting tired. I'm making sloppy mistakes. It is time for me to stop. But at least if I have a sign working on the thing, that's gonna be pretty big. So that's the expression value of this. I'm ignoring the type. Okay. What's wrong with this? So a let variable and a few other things. Or a function argument with two things. Oh yeah, there's absolutely no need for this to be It's not monadic. There we go. Parser here. And now this needs to be indented accordingly. Okay. Oh, that's because path name doesn't exist. This is path name of the path that is here. Name shadows the existing binding. That makes sense. Incomplete patterns, yes. Okay. Okay, we are at the point where we have warnings. Okay. That means we can start trying. Let's try this. If x equals 0, then f equals c. So here I am making a function pointer f point to function b. If x, the argument here is 0, update it to c, and then returns f, that function pointer applied to x, the argument here. And hopefully, with the assignment working, this should work. It happened at least. Okay. So we have function a, like this big function, takes an argument which is an int, I0 here. We assign to this f1 register the address of main b, which is a function. We assign I2 to 0. We assign to b3 the result of doing a comparison for equality between I0 and I2. We branch based on this boolean b3. If it is true, we go to label 2, otherwise we go to label 1 with different arguments, f1 and I0. In label 2, we assign to a new register f4 the function c, and we jump to the label 1 with the new function being this thing, because we have registered the fact that the value had changed, and now the invoke uses the register f5, which is the argument to the block, which will be f0 if coming, f1 if coming from this, if the if did not trigger, and will be f4 if the trigger. It works. It works. And we have enough that next week we can start doing basic code generation with just int characters and boolean. We don't have struct because I'm missing the assign to fields, but otherwise we have it. We have the lowering into AR in a week. Oh god, 7 hours. Oh god, it's 3 a.m. Okay, I'll stop here. But we've made so much progress. I just need to figure out how to do this absolute monstrosity that is the set field recursively thing. Yeah, I'm not sure how to do that. That field, that whole field update thing Monstrous. And I need to also think about a way to integrate it with like down the line array index expressions and stuff. But we're not there yet. Okay, I'll stop here for the evening. I'm happy still with the result. That's a lot of progress. I'm too tired to think of a good commit message. So it's gonna be very basic. Almost done with IR lowering. Yay! There we go. And yeah, I'm gonna stop here. The only thing we are missing at this point, the only thing that we are able to generate from the analysis phase that we are not able to lower into the AR is the assignment to the field of a struct. That's not too bad. Next week we can start the code generation. And then we will have a full pipeline and we can start iterating because we are able to write things that we can compare. Okay, I'll go here. I'll go for now. I need to sleep and I need to not do as much next week. This was too much. Thank you everyone for tuning in, and I'll see you next week.